Good morning, everyone. Assalamualaikum warahmatullahi wabarakatuh. Uh, so, I would like to extend a warm welcome to everyone to our first Control and Instrumentation Engineering Forum. So, the forum brings together business and academic specialists to discuss current trends in instrumentation and control applications. As you probably aware, instrumentation and control are employed extensively in modern life. With the automation of the majority of our industrial processes and the development of autonomous modes in transportation, we are confronted with new issues in the present and the future. And additionally, as instrumentation device and control become more integrated as network technology advance, there are some recent challenges in the instrumentation and control, particularly in the context of process control that are worth discussing. So this will benefit everyone, but notably those who are working or either direct or indirectly associated with instrumentation and control. So whether you are engineers, or a student or learning instrumentation and control, or someone who teach or doing research in instrumentation and control. So today a variety of themes will be discussed by 6 presenters with diversity background. So we have the following excellent presenters. So the first, we have Mr. Tushar Kamerkar from Yokogawa. And then we have Professor Eric Feron from KAUST. And we have Mohammed Hafeez from Emerson. And we also have Mohammed Al-Halafi from Nozomi Networks. And we have Dr. Solomon AlMadi from Aramco. And lastly, we have Dr. Abdullah Al-Halafi from Aramco. So we would like to express our gratitude to our presenters for agreeing to offer a presentation in our forum today. So this forum will be divided into 2 sections with the 3 presenters in each. So we will have Mr. Tushar Kamerkar from Yokogawa presenting his presentation, and after that we will have Professor Eric Feron from KAUST, and then after that we will have Mr. Mohammed Hafeez from Emerson delivering their talks in the first section. So each presentation will last around 45 minutes, followed by a 5-minute question period. And we politely request that the audience refrain from asking questions during the presentation time, and to do so during the designated time. So following the 3 presentations, there will be a break from 11:40 to 12:30, and then we'll move on to the remainder of the presentation where Mr. Mohammed Al-Halafi from Nozomi Networks will give his presentation, and then after that, Dr. Solomon AlMadi, and then after that, Dr. Abdullah Al-Halafi. So before we begin with our first presenters, I would like to invite Dr. Mujahid Al-Daifala, Chairman of Control and Instrumentation Engineering as a host institution, to provide a quick welcoming word and introduction. So Dr. Mujahid, the floor is yours.
Thank you very much, Dr. Mohammed. بسم الله الرحمن الرحيم الحمد لله والصلاة والسلام على رسول الله أما بعد. السلام عليكم ورحمة الله وبركاته. Good morning, dear colleagues, professors, researchers, students. On behalf of Control and Instrumentation Department at King Fahd University of Petroleum and Minerals, I would like to express my sincere gratitude and welcome you to the first Control and Instrumentation Engineering Department Annual Forum. Moreover, I honorably welcome our distinguished guest speakers, Mr. Tushar Kamerkar from Yokogawa, Professor Eric Feron from KAUST, Mr. Mohammed Hafeez from Emerson, and Mr. Mohammed Hafeez from Nozomi Network, and Dr. Solomon Al-Madi and Dr. Abdullah Al-Halafi from Aramco. I would like to thank them for giving us this opportunity to hear from them, their valuable experience and their findings. Also, I would like to thank the organizing committee for bringing together such great practitioners and scientists. Also, sincere thanks for the excellent support provided by KFUPM Institute for knowledge and for knowledge exchange. I hope that the first CIE annual forum would be able to achieve its objectives in providing an interesting knowledge for academician, researchers, and practitioners. There has always been a gap between academia and industry, and to bridge such gap, it is necessary to bring researchers and practitioners together and create an effective discussion and end up with applicable findings, which is the main objective of this forum. The theme of this year forum is recent advances in process instrumentation and control. The topics of today's forum covers variety of interesting subjects like process digital twin, self-duplicating robotics, sensing technology for plant digitalization, industrial control systems, cybersecurity threats and protections, and digital technologies for transforming construction capital projects in the petrochemical industry. I look forward to the rich discussion that we will have today, and we count on your participation and your sharing of best practices. Your contribution to this forum is highly valued, and I believe will be truly impactful in our endeavor. Finally, at the end, I would like to thank you all, and I will give the floor again to Dr. Mohammed Mzir to introduce our first distinguished guest speaker.
Thank you, Dr. Mujahid, for your welcoming words. Yeah, so as it's planned, we will have our first presenters, Mr. Tushar Kamerkar from Yokogawa, presenting his presentation about process digital twin. So I would like to give a brief introduction to all of you about Mr. Tushar. So Mr. Tushar has around 15 years of experience in oil and gas industry with a strong simulation background, both steady state and dynamics. And he has led and delivered various process engineering projects through different consultancies from India, Southeast Asia, and Middle East. And Mr. Tushar has considerable experience in mid or upstream simulation, working on projects such as production facility design and many other things. So, so I believe Mr. Tushar is here. So if you could activate your video and.
Hello everyone, Assalamu alaikum and good morning.
Yes, would you like to share your presentation?
Yes, let me share my presentation. Okay, I'm sharing it now. Can you see my screen okay?
Okay, yes, it's good. So, so the floor is yours, please, Mr. Tushar. You can start your presentation.
Thank you so much, Mr. Mohammed. And once again, welcome everyone, all the panelists, attendees. First of all, I would like to thank organizers of this forum for arranging this session and inviting us for this event. I would also like to thank all the attendees today for joining this meeting, joining this forum, and hope we'll have a great interactive session ahead. So as mentioned by Mr. Mohammed, topic for today's session, this next 45 minutes, is process digital twin. And we are talking about new advancements that have happened in process and control automation. And if we don't talk about process digital twin, then there will be a caveat in that. So I'll be talking about process digital twin, our views, KBC viewpoint on digital twin and our offerings, how it can help. So moving on, quick agenda for next 45 minutes is as follows. We'll have a quick introduction about KBC and its brief history. I'll not spend much time on that. Then we'll talk about general organizational goals, what requirements they are having, and then we'll briefly touch upon the typical challenges that we have seen these organizations are facing. Later on, we will talk about KBC view of process digital twin, its various components, what we think are essential, its working and how it's helping our industry to achieve better performance, better reliability, efficiently. And then finally, as Mr. Mohammed mentioned, we will have some time for question and answers. Is the agenda okay for everyone? Any queries, any questions on that?
Looks fine, thank you.
Thank you. Right, so moving on with KBC introduction. Sorry. Yeah. We have been in industry since 1979, so it has been 43 years now. And the founders of this company, Mr. Krikorian, Bryce, and Close, as indicated here, are all world standard technical experts who worked originally at Exxon, which is now called as ExxonMobil. Since then, we have generated around 20 billion plus benefits for our customers. And now KBC is not just a technology provider, but our consulting arm has simulated more than 350 process units, various process units, and delivered more than 1,000 plus optimization studies to various clients worldwide. Most relevant for today's session, KBC was recognized and awarded with Best Technology for Digital Twin in year 2022 by Hydrocarbon Processing. I'll not go in details. You can see there are many credentials already available here. So I'll just move on to quickly talk about KBC's history, briefly touching upon KBC history. As mentioned earlier, the company was founded in 1979, primarily performing yield and energy improvement studies for refinery and petrochemical plants. In 1998, KBC purchased Profimatics, which was a rigorous reactor modeling software, which forms a backbone for our refinery suite now. Lin of March is a well-known name for pinch analysis and heat exchanger networking methods in energy industry. And in 2002, KBC acquired Lin of March, bringing energy modeling and services to KBC offerings. 2 years later, KBC released its flagship simulation platform, PetroSim, and we will be talking about that in some time now. With this continued and further developments, KBC expanded in upstream sector, and in 2012 acquired a company called Infochem, who are providers of leading PVT modeling and thermodynamic engine multi-flash. Similarly, in 2014, with the acquisition of Visa, upstream production facilities and network modeling capabilities were added to KBC portfolio. And finally, in 2016, Yokogawa acquired KBC, and since then we are a part of big Yokogawa family. So that's about a brief history of KBC, how we have come along this way. Now, without wasting any time, I will directly go into today's topic, which is process digital twin. And as per the agenda, we'll be talking about typical organizational requirements. So as you can see on the screen, every organization's requirement can be segregated into 3 subcategories. It can be corporate, it can be management, it can be technical. Now, talking about corporate entity, the business goal for any corporate entity is to have improved profitability and have maximum return on investment. So whatever investment is done, be it new capital expenditure, be it brownfield assessment and developments, they need maximum return on investment, and that can be achieved by reducing operational expenses and increasing operational margins. These goals are then cascaded to managerial level, whose primary responsibility is to manage the facility better, do production planning, reduce the downtime for the plant while maintaining the plant safety as it is, for which they can have a quick and reliable tool which can support them in doing that, and which should help them in giving holistic view of their entire facility performance, so they can take better and well-informed decision, because they need to come up with quick solutions. So it's always advisable that they have these tools disposable, for their quick utilization. Now, if we talk about technical people like process engineers, operators, control automation engineers, their functional goal is to maintain the health of the facility, should monitor the health of the facility, ensure that it's working as planned. They should ensure that there are no bottlenecks in the system for the continuously changing throughput which is coming into the facility or plant. And in case there are any bottlenecks, they need to come up with some debottlenecking measures. And while doing that, they can also come up with some optimization handles. What we have seen, while doing all these tasks, some of the activities are quite mechanical and iterative in process, and that consumes a lot of productive time of all these engineers. So if we can have an effective tool for easy assessment of their facility, that can semi-automate, I would say, some of their manual cumbersome work, and then they can spend their their productive time doing some interesting activities rather than doing this mechanical iterative work. So these are some of the typical requirements that we have seen. There can be some specific problem areas that every organization can have, and that can be addressed specifically when we are dealing with case-to-case basis. Understanding these requirements, there are some challenges as well, and we understand that every organization, every company has got very complex architecture, complex structure, and they have got a defined work processes for delivering projects, managing their operations. And while doing that, there are many individuals are involved, and they are working in their own silos, we would say. So for example, here we have shown like 4 subcategories, like operations, engineering, design, commercial people, and R&D or technologist. So their aims are different. So operations are focusing on facility operation. They want to achieve maximum. They want to fetch maximum outcome from their facility. They need to manage the changing dynamic environment, and they focus on those aspects. While if you talk about engineering disciplines, there can be number of individuals, number of sub-disciplines like, process, instrumentation, civil, piping, control, automation, as you know that very well. And they sometimes support these operations, but they also analyze the plant performance in conjunction with operation people. They also liaise with R&D guys. They perform some in-house projects, design, revamp studies, and optimization levers are their specialties. If we come to technologists, their primary goal is to analyze and implement new upcoming innovative technologies. They can come up with the new work processes, which can improve the efficiency of the operation, improve the efficiency of the workflows, and they can aid and support operations and engineering design. And finally, when we talk about corporate, commercial, or planning people, their focus is on maximizing the revenue generation, with available systems. They do planning for future production. They do production scheduling, and these plans are distributed to all the other disciplines to make the goals in line with the overall corporate goals. All these groups, all these subdivisions have their own tools, their own software, their spreadsheets, and they are being used as and when required. And as you can understand, when this person is no longer with that particular organization, that knowledge, that resource is lost, and then everything needs to be started from fresh. So even though there are tools, they are satisfying the individual needs of specific departments, specific individuals, and that can be a problematic in some times. We have experienced that in our past experience as well. So to solve some of these problems, modeling or simulation driven approach can be an answer. And that is where the process digital twin comes into picture. So what is our view of process digital twin? What is KBC process digital twin? We think that even though the model can be used for many different purposes, that's our KBC philosophy, but these digital twins must be built or must be developed to achieve specific goals. It shouldn't be just another technological tool that is available in your organization. It should bring added value to each and every individual in the organization, be it facility manager, be it operator, be it process engineer, automation guy, or even the corporate entity. There should be something additional that can be brought by this process digital twin. It can help in enhancing the monitoring of your facility, and that is the key aspect for making any decisions when you are operating your facility for so long. What happens is we engineers tend to have our own models, our own spreadsheet, and whenever we require, we do the math calculation and come up with the results. So that creates a discrepancy within the organization. Different people are looking at different values in different time, which could be conflicting as well. So at such cases, at such instances, the process digital twin can act as a single source of a truth, which is available for everyone, which improves the visibility of the information, and everyone in the organization is looking at the same value at any time, whenever they want to. Some of the parameters which are not directly monitored, for example, if you want to know the pump efficiency, if you want to know the separation efficiency, compressor or turbine efficiencies, performance, power consumed, these can be realized using process digital twins. Twin not only acts as a monitoring tool, but it can also be used as an advisory system, which gives you the early warnings of any performance deviation, because it's continuously monitoring your facility. And this can be done in automated fashion as well. You don't need to do it manually by any of the operators or any individual. This we talk about when the digital twins are continuously working in online fashion, but the same models, can be taken offline, and they can be well utilized for what if analysis and what's best analysis. So if you want to do any sensitivity cases, any optimization studies, any bottlenecking, debottlenecking, that can also be very well done using the same models. You don't need to start building those models again, gathering data. It's readily available. Just subscribe to the latest model and perform your sensitivities, because that model would be up to date and reflecting your exact plant configuration. In addition to that, the same models have been used, and our own consultants are also using these models for profit improvement opportunities. So while developing these digital twins itself, we can come up with some profit improvement opportunities for your units. And then with online profit tracker, those opportunities can be tracked for sustainable growth. So as we mentioned, there are many uses with the same model, but then again, it is developed to cater to solve some of your specific problems. This slide shows a quick overview of what KBC Digital Twin looks like. So what you see on left is the visualization representation of the entire upstream production facility. But you can also drill down to individual equipment and visualize the key parameters of your interest. Similarly, for downstream as well, even the reactor units, the conversion units can be modeled with our rigorous refinery reactors, petchem reactors. Along with that, the energy consumptions can also be tracked in tabular as well as graphical manner. So visualization tool can be of any choice. We are agnostic with respect to using visualization tool. But what is working in background is our key simulation technology, and namely those are Petrosim, Multiflash, and Maximus. We will talk about it in detail, how our digital twin is working, how we are making this monitoring quite easy for our clients would be some of the next slides. Moving on directly in bit of detail about digital twin architecture. The slide shows the data and workflow, how KBC digital twin is working. So for any digital replica of a plant, the key and essential thing is fetching plant data in real time. So most of the operators, they have historian. Here it's mentioned as PI, but it can be any historian. We can also utilize the data available in LIMS. And through this channel, using our monitoring services, we can bring in the data within the simulation environment. So as you can see, the digital twin platform, which is a Petrosim simulation environment, has come beyond its conventional limits of simply being process simulation, and it has got many other handles which makes it easy to use in this digitalization era. So as we are talking about data fetching, the native connectivity of process historian makes it quite easy to connect with your historian. It can be any historian. You can connect to this data through OPC channel. If you have PI, it can be directly specified here. Using database, you can connect to other historians as well. But what we have seen is that operators have tendency to fetch historic data into Excel spreadsheet, and then they use it for for their analysis. So to make that enable, we have this add-in functionality wherein we can link with your Excel spreadsheet, any other form of database as well. Once this connectivity is established, the necessary equipment tags can then be configured in the same environment. So there can be two categories. One is for monitoring the process health, but the other can also be configured to monitor the instrument health, and I'll talk about that, how it can be helpful. Once these tags are configured in this historian connectivity environment, they can be mapped to individual streams so that simulation knows which value is to be passed to which individual stream. All this is one-time activity. You don't have to do it every time. Once this is established, you can simply go to this setting tab, wherein you can select a specific time period for which you need to fetch the data. Now, this I'm talking about is the manual process, but all this activity can be configured in automated way. So we can configure a digital twin, and we can specify a specific time, let's say 12 in noon, 8 o'clock in morning or evening, depending on your shift timings, where the simulation or the model will open automatically. It will fetch data for last 24 hours, 8 hours, whatever time period we have to specify. It will pass that on to simulation, perform simulation, populate the results on desired dashboard, and save the file and close it. So without any human intervention. So all the results will be ready for your review and for the necessary action. So this is about data fetching. Once the data is fetched, we cannot directly use that data because, as you know, there can be disturbances, noises, erroneous data. So data conditioning is another essential and mandatory step within this workflow. And that also can be achieved within the same digital twin environment. Petrosim has got data conditioning capabilities which can highlight out of range values if there are any erroneous plant measurements. Once those out of range or outliers are identified, appropriate parameter values can be considered automatically by the model because we can configure that logic within the tool. And these kind of data quality checks are performed for every run. So you don't have to worry about poor data quality. If there are any outliers, the user warnings can also be issued, can be triggered automatically based on these pre-configured logics, because we do have got workflow functionalities available in these tools. So this assures the data that is coming into the model is good and you don't get any random or trash results out of the model. Other aspect that we have learned over the years is, as the facility is operating for some time period, it tends to deteriorate, and then model needs to be recalibrated to mimic that performance over a period of 6 months, 1 year, 2 years, like that. So we do have functionality for checking the model performance. We call that model performance indicators, which is essential for model quality assurance. So if these indicators start deviating out of the given tolerance, it's the time for model to be recalibrated. So with this validation, you get the correct data in, but that is also not sufficient, because, as you know, the plants are not operating in steady condition. There are some lags, there are some inherent holdups involved in the system, so which cause imbalance. So at any time, if you take the balance across the unit, there will be some there will be some gaps. So whatever is coming in will not go out at the same time. And that is where we need to reconcile data. This is one of the activities that plant engineers and operators do on daily basis. And the usual way to do that is sometimes we dump all the error, all the imbalance into one particular stream, and then we go ahead. But in this digital twin environment, the data reconciliation can be done automatically. Once you define the inlet and outlet streams, the overall mass balances are done for every run. And then your material balance report will be ready for your review and further analysis. The imbalances and the distribution can also be seen and highlighted with different color coding here. This can be also helpful in identifying reliability or accuracy of your instruments. So as I mentioned, there can be one set of data which can be used for process digital twin, but there can be another set of data which is fetching from historian, which can be used for your instrument reliability. So it can give you an indication if your instrument is going off or if it needs recalibration. So in some cases, these reconciliations are sufficient when they are done on overall basis. But when we talk about refinery units, sometimes we need to perform individual elemental balances as well. And that functionality is also available within the data reconciliation. So once the data is reconciled, now we have this sanitized data ready to be sent to the simulation environment, where all the independent variables can go to respective streams. Simulation can perform and can give us the results. So when we are talking about simulation environment, be it upstream or downstream, digital twins can be developed for any part of the supply chain using the same technology. So what you are seeing on screen right now on left-hand side top is the digital twin, or what we call as integrated asset model for upstream production and processing facility. So on the same environment, you can have entire network of subsurface and surface flow lines, and that is connected in real time with your topside processing facility. It can be a simple GAUST, it can be additional stabilization, compression, or even LNG or dew pointing unit. So everything will be available on the same platform without running between different tools. Similarly, a high level or even a detailed digital replica of refinery petrochemical plants can be configured using rigorous kinetic reactors, which we are doing. Many of our clients are already utilizing these capabilities and monitoring their plants for better performance. And beauty of this tool is everything is underpinned with unified thermodynamics. Why it is so important? What I personally experienced this, specifically talking about upstream environment, upstream production facilities. There are a number of subgroups like reservoir group, like wells, flow assurance, facility management, and they have their own responsibilities and aims. When reservoir group is doing production forecast, they make some assumptions, and they use minimum components, like their interest is just 5 to 6 components. But when it comes to flow assurance guys and production facility, they need to know a detailed fluid composition and its thermophysical properties, because the equipment selection and its performance depends largely on the behavior of this fluid. So while doing this, we call it lumping and delumping activity. While doing this lumping and delumping activity, it creates a disconnect, because the thermodynamics used by different group gives slightly different values. When it comes to topside facility people, they will see this disconnect, which leads to sometimes erroneous results, sometimes over-conservative approach, which is in turn costing higher capex or opex value. So with unified thermodynamics, we avoid all these over-conservatism, we avoid all these uncertainties, and you have seamless flow of all the thermophysical properties throughout the entire supply chain. And this is available, as I mentioned, for both upstream as well as midstream and downstream facilities. So what consists of these digital twins? Let's quickly talk about the basic building blocks of digital twin. And as you can see, they are primarily comprising of multi-flash, Maximus, and Petrosim. So depending on which industry or which area we are developing a digital twin, either two or all of these can be utilized based on one's requirement. So what is multi-flash? As you know, success of any simulation tool or any calculation depends on how accurately it can predict the fluid behavior, and its thermophysical properties over the entire operating range. So multi-flash is a robust, rigorous PVT modeling engine, which can provide you the compositional data, and it can handle any phases. So I'm not sure if you are aware, but multi-flash is not only used by our technologies or our simulation tools, but some of the leading simulation technologies provided by other vendors are also using multi-flash as their background thermodynamic engine, which forms a backbone actually for ours as well as their simulation technologies. The next tool is Maximus, which is a compositional thermohydraulic life of field simulation. So it can handle a very complex network of flow lines. There are some unique features and functionalities which can be used for gas lift operations, further optimization, hydraulic potential. So you can model entire reservoir, the completion, production network, daisy chain networks, and perform various analysis, sensitivity cases using that. It creates a better understanding of main constraints on operable or achievable flow from production systems. And it also helps in improving workflow between various engineering disciplines. It promotes the collaborative approach. So data flows seamlessly and there will be less hazards. The next tool that I'll be talking about is Petrosim, which is our flagship simulation engine. Petrosim is a quite advanced time-based process simulation. It can be operated in 3 modes: steady state, dynamic, and life of field. So life of field is basically discrete steady state simulation. So for example, if you want to run multiple cases over a period of time, you can do that through the same environment. You don't need to save different cases. Again, for upstream scenario, if the production profile is available for 20 to 30 years, the usual approach is we choose the governing scenarios like maximum GOR, maximum GLR, maximum liquid production or oil production, and then we run those specific cases with some assumptions. But with this life of field functionality, you can simply plug in the production profile data received from your upstream discipline and run all those year simulation in one simulation instance and visualize those in a graphical manner. So that gives you better visibility of how your facility is going to operate. If I talk about downstream application of this life of field, specifically catalyst deactivation, which can be configured, which can be analyzed using this life of field functionality, which gives you cumulative result over a period of time as well. Petrosim has got some purpose-built utilities, some of which we saw just now, the reconciliation and data cleansing capabilities, and a few of which we will be seeing in subsequent slides as well. Reporting is quite strong in this tool. We can have multi-case reporting, which can be stored in a database which comes along with the Petrosim. And workflows functionality enable user configure their own customized workflows with user alerts and configurable logic. Petrosim, as I mentioned, has got strong connectivity with process historian, and we have very tight integration with Excel as well. So some of our clients are directly using Excel interface to run the Petrosim digital twins or simulations without actually looking at the actual model. And last but not the least, Petrosim comes along with its own database. So all these cases, all these analysis that you are doing, even if we are using a digital twin in online mode, all these results are stored in SQL database, which comes along with Petrosim, and any user can access that at any time if they want to see it. So it's not just a result, even the simulation models will be available if they want to analyze it further in deeper details. The next very important aspect that KBC Digital Twin is offering is integrated process and utility modeling. Petrosim has got capabilities where utilities like instrument air compressors, the steam network, including its boilers, steam turbines, desuperheaters, different levels of steam headers, along with gas turbines if you have, which are driving your compressors. Everything can be modeled alongside your process, and they are connected in real time. So your demand and supply are connected in real time. So if there are any changes in process side, those will be reflected on utility side as well. And why this is important, I would like to mention one example here in my past life. We were performing an optimization activity for a process plant. We finished that quite well, and it was the project was about to finish. But when the client checked on the utility side, they realized that their existing utility installment is not sufficient to cater these added requirements, and that delayed the project execution by a few months, which obviously costed them some handsome amount. So if that would have been studied in conjunction along with process and utility, it would have saved them the amount that they have lost because of these delays. So that is why it is very important. And again, now these days we are talking about energy efficiencies, emissions. So all these aspects are very well covered on this same platform under the umbrella of Process Digital Twin. Moving further, just a quick highlight. We are supplying all the technology that covers end-to-end solution, right from production till the final product. So we talked about multi-flash, Maximus, Petrosim, but we do have some other sub modules available within the tool, as like FlowVax, which is specifically used for prediction of wax formation and deposition in pipelines, Super Target for pinch analysis, heat exchanger networking. And then we have some other tools for energy management, production accounting, and scheduling as well. So this is just a quick touch on available technologies that we have. Now the simulations are done. All the independent variables are pushed into the simulation, and the results are stored or the results are available in simulation environment. But what is of our interest, or what is of corporate interest, is to see some of the key KPIs which matter the most. And that also can be done within the same digital twin environment. So desired KPIs can be configured in same environment. If those KPIs are not directly measurable, they can be calculated in the same environment, and those inferred values can also be available in that Petrosim environment. Now, these KPI values are stored in KBC Explorer, and those can be trended, or those can be available in graphical manner through KBC Explorer. So if process engineers can interact via this KBC Explorer, they can run the models, they can visualize and analyze the performance on this if they don't want to go to the high level or corporate KPI. Similarly, they can drill down to individual equipment as well. So if you want to perform any bottleneck identification, that can be readily done using these digital twins. So what I'm showing here is just an example for heat exchanger, where there is a design duty is plotted with dark blue line. And what you see in light blue color is the actual operation of that heat exchanger. So as you can see, it's approaching its threshold limit. So you can take some proactive measure before it reaches its threshold value. Similarly, there can be indications if some of the parameters are exceeding the usual operating envelope, and that gives you warnings on the dashboard, warnings in the KBC Explorer as well. So it helps in providing you advisory and guidance for your facility operation. Another example, quick example for downstream here is, you can see there are two charts. The left one is for light naphtha, whereas right one is for decanted oil. And for these refineries, we plot LPs, linear programming are used for planning purposes. So what you are seeing here in dark blue color is the actual measured yield of light naphtha. The light blue color is what simulation is predicting, and the green or the greenish is what is estimated by LP. So all these seem to be in sync for light naphtha in this case. However, if we see the chart on right hand side, which is for decanted oil yield, you'll see simulation and measured value, the actual plant operation, are in sync, but your LP is off. So this gives an indication that you need to update your LP vectors to have accurate forecast and prediction for your planning purpose. Further, as we mentioned, unit dashboards can be configured alongside other historian or other historic data, and then expert users can perform deeper analysis via Petrosim, the actual environment, or through KBC environment. So that completes a cycle. Once these KPIs are available, they can be stored in a central repository and populated in desired dashboard or your ERP system. So along with this, we are also providing, as I mentioned, online profit tracker. The same digital twins can be used in closed loop environment as well. We do have offering called dynamic RTO, where the same digital twin model can be utilized to perform real-time optimization. With this slide, I have come to end of my presentation. I'm just being cautious of time. Yeah, we are 44 minutes, so I think we are on time. And now the floor is open for questions and any open discussion. I'll be happy to answer your questions.
Yeah, thank you, Mr. Tushar, for your presentation. It is very nice to hear from you about the process digital twins. So yeah, so if you have a question for Mr. Tushar, yeah, we can have like one or two questions, like quick question.
I think I can see Mr. Mujahid has raised hand. Please, you can unmute yourself.
Yeah, so we got one question from Mr. Abdurrahman Al-Otaibi in the chat. So he asked about if the DT approach that the KBC utilize is fully autonomous or not.
Yes, absolutely. Absolutely. As I showed, sorry, all this workflow that you are seeing is configurable in autonomous way. So you don't need any individual intervention. So all this data fetching through historian is automated. So at specified time, the data will be fetched in. The data validation and reconciliation is done before passing it to the simulation environment. Simulations will be run automatically and KPIs will be populated on dashboard. So any operator, any process engineer will not have to intervene any of these processes. It works on full autonomous basis.
Okay, thank you, Mr. Tushar, for your answer. We got another question from Mr. Hussein Al-Juman. He asked, what are the most common use cases for digital twin in industry?
Okay, so most of our clients are using it for refinery operations. First use case is monitoring of health. So if all the unit operations, because as you can see, you can go into as much detail as possible. You can even go to individual equipment level. So you can track your compressor efficiencies. You can track your product qualities. You can track your emissions, your energy consumptions. But in refineries, most of our clients are using it to keep track of conversion yields, the product yields, and they are tracking it with respect to LP, because we do have LP utility as well. So LP vectors can be generated, and all these are available on a unified dashboard. So there are multiple use cases, and as I said, depending on your specific requirements, we can have KPIs. Like for LNGs, we can track conversions, the C2, C3 recoveries. For FCC, we can track conversion. We can track the catalyst deactivation. So it gives you idea how fast you will have to replace your catalyst. Regeneration is to be done. Not for FCC, for hydrocracker, because FCC it's continuously regenerating. So use cases are, there is no limit as you can use it for whatever purpose you need.
Okay, thank you, Mr. Tushar. So is there any more question for Mr. Tushar? Okay, we got another question from Mr. Mujid Oyedeji. So he asked, to what extent is machine learning employed for improving process models?
Okay, so there is an initiative going on within our organization where we are utilizing advanced analytics, artificial intelligence technologies for recalibrating the reactor models. So once as I mentioned, the model performance indicators are showing some off trends, the AI will kick in, it will come into picture, and that will do the auto calibration for the model with suitable data set, and then your model will be readily available. So even that calibration activity becomes independent of human intervention. We can also club the advanced machine learning techniques along with this digital twin as well, because we are technology agnostic. We can link with any other technologies that you already have, and that's because we believe in embracing rather than replacing. So we are not asking you to replace anything, but we will support your existing infrastructure and architecture because you already invested in that. So we are technology agnostic as well.
Thank you, Mr. Tushar. I think we have enough questions for Mr. Tushar. And again, thank you for this excellent presentation. And we can end this presentation now. Okay, thank you, Mr. Tushar.
Thank you.
Thank you. So that is a very nice presentation by Mr. Tushar from Yokogawa, and our next presenters is Professor Eric Feron. I believe Professor Eric Feron is here with us already. So I will also read a quick review of his biography. So Professor Eric Feron is a professor of electrical, computer, and mechanical engineering at the King Abdullah University of Science and Technology in Saudi Arabia. And Professor Feron also has been in many other academic institutions in France and in United States as well. And he is also a research engineer at some of the one of the research facility in France. And Professor Eric Feron interests are using fundamental concept of a control system optimization and optimization theory and computer science to address problem in aerospace transformation engineering, including air transportation, area robotics, software and system certification, and many other interesting things. So today, Professor Eric Feron will present about self-duplicating robotics experiment with software and 3D printers. So I believe it is a very interesting topic. So Professor Eric Feron, the floor is yours.
Okay, thank you very much, Dr. Mohammed. Salam alaikum, everyone. My Arabic still works with quite a bit of an accent. And on top of that, my English itself comes with quite an accent. Being French was my original condition. Today, so I will talk about self-replicating robots. I have decided to change a little bit the title in order to focus on the kind of questions that I am interested in today, and that remains perfectly within the scope of what I wanted to talk about. A couple of words before I go into the presentation. So at KAUST, we have a range of activities, fundamental science, engineering, and questions that are sort of in between. The laboratory that I animate is the Robotics, Intelligent Systems, and Control Laboratory. This laboratory was founded by Professor Jeff Shamma back around 2014. And upon the departure of Professor Jeff Shamma, I inherited this laboratory. I loved the acronym. I loved the people inside. And so I decided not to change anything. My colleague is Professor Shinkyu Park, and he's also interested in the general area of robotics and control. And has fairly consistently shown what he's capable of doing. While my training is in aerial vehicles, his is about underwater surface vehicles. So overall, we have a wide array of possible activities, and we are blessed to have students from all over the world, not forgetting KFUPM. And within KFUPM, we have alumni from your own department, working either as students or postdocs, and it's a true pleasure to be hosting them as very productive members of KAUST. So the kind of things that we do in academia sometimes can be seen as a little bit off compared with today's practice and the movement of today's activities. And this is on purpose. We operate at what we would call the basic research level, as opposed to maybe the applied research. We try and think of experiments whose relevance might be not now, but in 20 years. That said, we are always interested in hearing presentations such as our previous speaker, who talk about the important activities taking place today. And to be honest, all the activities that relate to digital twin encourage me, for example, to keep teaching problems of what I would call filtering and estimation. And instead of calling the systems that I'm trying to estimate or the system that I use to estimate an estimator, I changed the name and called it digital twin. And the students love it, and they immediately feel better the relationship of what we study to, in particular, their professional opportunities. And so I again thank very much industry speakers to be able and talk about what they do, because it definitely influences what we teach, how we teach it, and it keeps us our faith into thinking, okay, we may not be able to replicate a complete manufacturing plant, refinery, oil plant, but at least we can follow the spirit of what goes on. So that said, here is a presentation about things that are pretty far out. One of the things that 3D printers have brought to my mind is the ability for the 3D printer to print many different things. 3D printers can print metallic parts, they can build plastic parts. In some research that I know of, it can even print circuits. And so what happens is that printers bring manufacturing orders of magnitude closer to us, simple humans working in our offices, than it used to be. It used to be that printers could do, the printers did not exist, or there were sophisticated things, and there were lots of in-between as far as what we needed made and what, and us. And so the machinery was complicated, was inaccessible. And, but then with a printer, things become much closer. And we can say that the printer can print things for itself with a little bit of imagination. And so we get into these questions of self-repair. Now, why is the idea of self-repair important? Well, for many reasons. that I will now discuss. I will discuss the motivation for my presentation, the goal that we've been seeking, the experiments that we've been doing, some mathematical modeling, simulation examples, and then validation efforts followed by conclusions and future work. So why are we talking about self-sustaining robotics? Well, we know that today the planet is making a lot of things. Planet Earth, including us, is making a lot of things. And there is this feeling that, well, automation is progressively taking over many of our activities. And that, you know, robots are progressively replacing the human as far as whatever manufacturing activity takes place. However, if you take things from a very futuristic viewpoint, human lifespans are insignificant compared with astronomical timescales. The human body is adapted exclusively to conditions on Earth. People talk about terraforming the moon or Mars, but there is no particular reason why that would be an easy task. And so we are thinking that maybe the future, for example, of manufacturing on other worlds than our world may result in a self-replicating, self-repairing robot colony. And that colony may be there to sort of further extend our ability to do space exploration, and humans would not be there to sort of do much. Personally, I believe that, you know, despite what people say when they say we want a human on Mars, I think it would be very difficult on the one hand, and that although the human as we are is not on Mars, yet the human spirit is already on Mars, since we've been able to launch robotic capabilities there. But again, those robotic capabilities keep going for a while, and then they die. For example, the small robot Spirit, if my memory is correct, died because there was too much sun on the solar panels. So what would be needed? Well, maybe we should have thought about adding a robot that would clean the solar panels. Okay, but then eventually the cleaning robot on the solar panels and the robot itself would wear out. So we would need other machinery to take care of those robots. And the idea is, as I said, eventually we need to create an entire self-sustaining and robotic ecosystem to take care of itself. And the further we go from Earth, the more important that is. So there are also opportunities for self-replicating robot colonies on Earth, and to, for example, colonize hazardous zones like the ocean, North and South Poles, and desert. In Saudi, the empty quarters, whose size is greater than, for example, France, by at least 20%, is a place where humans can barely survive without the proper equipment. And so thinking about a self-sustaining robotic community operating there for mining or other kind of activities may be also relevant. In terms of background, self-manufacturing systems have been around for a while. People like John von Neumann, who is credited also with the invention of the first computer, was the first to formalize a theory of self-reproducing automata. He approached the subject from a logical viewpoint and introduced the essential question: how can reliable systems be constructed from unreliable components? Okay, so working with these self-reproducing automata that are also called cellular automata theory. So he looked at automata that can achieve self-replication and where you can have self-reproducing machines in software, and that's what we see mostly or only today on the one hand, but then he also had in mind self-replicating machines that are physical objects in a physical space. The kinetic automata that are the self-replicating physical machines involve several challenges related to fabrication and assembly that do not apply to cellular automata. However, it is still interesting and useful to think about things like cellular automata and things that basically reproduce themselves. For example, in the case of aviation, we have been looking at the idea of running and flying an airplane with multiple computers where the computers are not very reliable, and whereby sometimes some essential computer functions for an airplane, which includes control, guidance, monitoring, etc., need to be, if I may, reallocated to new computers or to computers that are still working if the computer they have or that houses them dies. So there is a lot of value in looking at self-replicating software. There are there are interesting challenges coming with that. We have dealt with some of them, but again, the physical world is a little bit different. A computer can do a copy-paste operation, taking a program and copying it and then porting it over to a new computer, and making the program work in a way much more easily than a human can sort of say copy-paste itself. In fact, a human can copy-paste itself, and so it's more about the robots that have trouble copy-pasting itself. For humans, we have this built-in self-reproduction capability. When you think about it, we are made of a bunch of cells, billions and billions of cells, and each cell is sufficiently intelligent to replicate itself on demand. As a result, who we are today on a physical basis is extremely different from who we were a year ago, as far as the material basis of who we are is concerned. You know, our skin is completely new compared with a year ago. Our guts have changed probably 20 times since a year ago. I may exaggerate a little bit, but it is above 10 times, okay? Our brain cells, which change on a slower basis, still do change. okay? And so there are many parts of ourselves that sort of have self-repaired, self-reproduced at a very low level of cells in such a way that, well, we are essentially new compared with, again, a year ago. As I said, the prospect of having now 3D printers brings the possibility of looking at one case of self-replicating, self-repair machines. Since, as I said, in principle, there is no limitation for a 3D printer to print its own parts, though some of these printing ability, for example, printing circuits, is still far out and at the basic research level. For example, from Professor Jerry Chi at the Georgia Institute of Technology. Another person who thought about self-replication is Richard Feynman. Richard Feynman asked himself about the role of degradation of a machine at the time of its self-repair. And the question is, for him, was to see whether a machine can fabricate a more miniature copy of itself. These talks happened in the 1950s, and they were, in a sense, fairly theoretical thoughts back then, and remain fairly theoretical today. And he said, we have a problem. If we want to make a miniature version of, if a machine wants to make a miniature version of itself, it must improve its precision at the same time as it shrinks. Okay, so what we see are fairly general conclusions about system self-manufacturing and within the context of activities that we are witnessing today and manufacturing behaviors, miniaturization being one of them and benefiting all of us. Computer that is currently operating our cell phones is more powerful than the much larger computers that are used in order to fly the 737. So miniaturization with augmentation of power is also part of the important manufacturing behaviors that we're interested in seeing. So we would like to build a theory for robotic self-repair, but it's a theory. We need to do experiments, and we need to do experiments in a relatively narrow context. So what we are hypothesizing is that a 3D printer is able to repair itself as far as a fairly narrow set of repairs is concerned. A 3D printer is made of many elements. It is made of columns. It is made of motors. The motors turn some belts, and then the printer head is moved by those belts in order to print pretty much anywhere on the printer. And what we are interested in is the following question. Can we start with an imperfect or degraded components on the printer? And can the printer, if I may say, repair itself? That is the printer capable of producing a component that will replace the worn out component by itself, and despite the fact that, well, it operates with a degraded component? Okay, so the experiments we did are of again very simple nature. In this case, we looked at a recursive activity whereby a printer is asked to print the part it needs with the help of the degraded part, and we try and see if as we recursively use the part that's printed to replace the worn out part, if there is any hope that the printer will eventually repair itself and make itself new. Okay, at least as far as that part is concerned. So this is the idea. We took a printer and we just did something very modest. We just said, the printer has pulleys. The pulleys are used by electric motors to move the printer head. What happens if we replace the pulley by a degraded pulley? There are many ways to describe a damaged pulley. What we did is, as you see, the pulley, instead of being round, was replaced by a triangular pulley. That may sound shocking, but we thought that that would be an interesting case. And what we asked is, again, to print a replacement pulley with the degraded pulley and see what we get as we iterate that way over a couple of times. Here's the experiment. Here's the experiment. So we run the printer with a bad pulley. We asked it to print the pulley we needed to replace this bad pulley. Out came the picture in the middle, which showed a much more round pulley, okay, which we again used to replace the bad pulley. And then we iterated once more. And after 3 iterations, what we ended up was a pulley that is basically impossible to distinguish from a new pulley, meaning that the distance or the difference between the last pulley that we used is virtually indistinguishable. So what we say is that in this particular experiment, which is again very restricted, okay, but remember, we're starting from pretty much nothing, okay, in terms of science, except the fundamental studies made years ago by von Neumann and Feynman. In this case, the 3D printer kind of achieved self-repair, okay, was able to bring itself from worn out to new. And what we wanted was to see how we can build a little theory of this. And for that, we started working with models. And all this is preliminary and will be presented at the American Control Conference this coming June. But so we modeled the experiments we did using, elementary math. And we started by modeling the pulleys themselves. So a pulley that acts on a belt is undistinguishable from its convex hull. So if the pulley, even if the pulley has what I would call concave zones, okay, those concave zones do not matter as far as the printer or the pulley effect on the printing process, okay? And so we can assume the pulley is convex. And we can say that two pulleys are equivalent if they share the same convex hull. So what we did is, with this modeling of the pulley as a convex object with possible edges and vertices and things like that, in order to build some predictive capability, we needed to understand how a pulley of a given shape acts on the belts that move the printing head. So for that, we needed to relate the angle by which a pulley rotates and the displacement of the printer head. It turns out that we can define for any pulley what we call the instant displacement done by the pulley, which is by how much the belt moves given how much the pulley rotates. When the pulley is purely circular, the belt moves strictly proportional to the pulley angular displacement, okay? But again, in general, for these pulleys, we may not have this relationship if the pulley is worn out, and probably many people have felt that when you pull a rope and the rope goes through a block and the block is used, or when your car, for example, has a damaged tire rim, then the car starts having a more chaotic behavior, and vibrations ensue, and the phenomena are pretty much rooted in the same issue. So what we did is then in order to build a mathematical model of what goes on, we take a pulley's model, we find its convex hull, then we find by how much the printer head moves as the pulley rotates, and then with that, we can simulate the printing process. We have, depending on the kind of object we have, which, remember, represents a form of damage or to the printer, depending on the shape of the object we have, how may I say, the speed at which the belt moves can be very different from the speed at which the pulley rotates. And you can see some examples here. For example, a triangular pulley yields belt behaviors that are a little bit seesawed, a little bit like this. A square pulley is a little bit like a triangle, but there are more facets to a square than to a triangle, so it does the same behavior, but in the same general shape, but at a different frequency. And then, if you think about a heart-shaped pulley, okay, where although the pulley is shaped like a heart, the behavior of the pulley is the same as the convex all of this heart, then you can get, again, other behaviors. And so this is important in order to, based on this, predict the characteristic of the shape that will be printed afterwards. We don't change the software in the printer. We just print pulleys with bad pulleys. And so we looked at and built our simulation to try for a large number of simulation examples in ideal shape, triangular shape, large triangular shape. So the pulley doesn't have the right shape and is doesn't have even the right size. And then also a pulley that's shaped like an oval. Okay. So in order to help with that, we made a small technical assumptions about the number of steps per revolution of the stepper motors that we use. And this is in order to understand better the relationship of the value of, well, if I may say, the printer belt advancement rate on the one hand, and the resulting shape on the other hand, the resulting shape of what is being produced. So, for example, we start with a triangular pulley, we get a convex hull, we get its sort of instant displacement, so rate of displacement of the pulley, the belt supported by the pulley versus the angle that the pulley has. And then we said we need to print this. Okay, so we set that using standard STL files for the printer, and we look at what this triangle was able to print. And it turns out that if you look at more details, okay, what you get is you get a printed pulley, which is not quite a circle, but already stops looking like a triangle. Okay, as a result, this is quite encouraging, and this is quite encouraging. As I said, the model was tested on using a circular pulley instead, and then what we see is that when we have a circular pulley and we want to print a circular pulley, we have basically a fixed point. The pulley that ends up being printed has the same shape as the pulley that was used to produce that shape. As you see, if we pick a too large a triangle, then we get other behaviors. For example, when we ask to print a certain pulley, again, the same circular pulley, what we get is that triangle wanting to print that pulley actually yielded something which is not quite ideal, but an elongated shape. Okay, so the same thing happened when we print and when we start with, an oval pulley. I mean, all these are sort of scenarios of degraded pulleys. Okay, and we asked that degraded pulley to print a replacement pulley which is strictly circular. And what we obtain is an iterate which looks a little bit like another kind of ovaloid shape. The question is our simulation matching reality? That's sort of a first elementary model. We could call it a digital twin of a printer printing itself. And the question is, does the simulation work? So for that, we repeated the experiments that we had done before, and we put side by side our simulation with the iterative process of a printer printing one of its own parts. That own part is housed in the printer and then is used to print the same part again. And what we see here is that the simulation we've built based on simple geometric consideration sort of has the same kind of behavior at what is experimentally observed. This is a form of validation of the model. We don't know what we're going to do with the model yet, but it's a validation of this printing model. We started with also a printer where the pulley has worn out and become a very small circular object as opposed to a large circular object that we had before. And again, we change only one pulley, okay? But as we go through the printer printing itself or its own part using a small pulley, the small pulley becomes an oval, okay? It becomes an oval on the next iteration. And what you can see is that the experiment and the simulation are giving sensibly similar answers. And as, again, this part is used to print the next generation pulleys, what you see is a recursive series of pulleys that look increasingly circular. So we can say in the mathematical theorem that yes, it definitely looks like a circular pulley is a stable point of the printing process. Whatever shape we start with, we converge to that stable point. Now, of course, it makes it a little bit difficult to think of a printer part as part of the state space of the printer. But you know, if you do that and you try and think in terms of control systems, it is a stability kind of result, whereby we can say a well-working printer is a fixed point for wherever we start as far as printer damage is concerned, and the printer damage is just at this point what I would call damage pulleys. Okay. Another validation, we started with quite an extreme pulley, so we made it like just a straight bar. Okay, and we said, okay, so print something circular, and the bar, okay, so this pulley, which is very, very oddly shaped, okay, and quite challenging, if I may say, you know, it's very worn out part. Well, progressively, again, as we recursively replace the original part by what has been printed, and so on and so forth, we end up finding that, again, the part that is iteratively printed converges, again, to a new part. Now, does this generalize? How does it generalize? What kind of convergence rates do we have? Form what I would call like interesting new problems that have not been explored before. Again, we are very lucky to have this world of 3D printers that allows us to run these experiments. And what we believe is this constitutes a good first step towards studying the ability for robots to self-repair. 3D printing offers us, as I said, a very good support tool to study these things that was not necessarily available even a few years ago. And we hope that the experiment that we performed will motivate further research in this area and eventually contribute to preparing colonies of self-repairing robots where they may repair themselves or they may count on another robot to repair them while they repair the other robot. What we did recently was to illustrate this point was to acquire a pair of manipulator robots that would collaborate with the printer, whereby the pair of mechanical arms would be sort of moving the part printed by the printer into place. And at the same time, the printer would be able to produce the parts that the robots need in order to keep operating. So I hope that this presentation is to your liking, and this is it. I am ready to take questions.
Thank you, Professor Feron, for the very interesting presentations. So we might be able to have like one or two questions from the audience. Okay, I think while we are waiting for a question from the audience, I'm a bit curious about what kind of like the state of this transforming shape of pulley. Is it going to be some a weird mathematical object, or maybe it's like something?
So we worked on that. So in this case, even for a single pulley, describing what the state of the pulley is, we're describing, capturing mathematically the shape of a pulley can be a little bit of challenging, because you know that the shape of a pulley is sort of something of a continuous nature.
Yes.
And so, it's like even at the level of a very simple experiment, we already have representation problems. And for now, what we did in order to build our simulation was to characterize this shape using basically the convex envelope, and then we would then discretize this convex envelope. One of the pictures that I showed like a discretization. For example, for a triangular pulley, the discretization would be like the three tips or the three vertices of the triangle. Then for a round pulley, press in a little bit like counterintuitive way, the discretization of the round pulley takes more data than the representation of the triangular pulley. So what we have is like, somehow the more ideal things are, the more parameters it takes to get that. So again, it's what I like about this research is it, as you said, it sort of questions even our ability to represent state space, inability to sort of eventually get our traditional feedback system, since we're operating something as a feedback, representing that as a feedback loop of sorts. And just that was kind of fun, finding the model, finding the transformation. I should add that we have been working not only with a simulation, but also with closed form mathematical models that required further simplifications of how we represent the objects that both repair and are repaired, and interestingly enough, we got like similar convergence results for our mathematical models as those we saw in our simulations, and those matched also what we saw happening in our experiments.
Yeah. Okay. Thank you. So we have like a few questions from the audience. So this is Mr. Marwi Al-Harbi asking about how the printer will identify the faulty part, and also can the repair model improve itself with each iteration with some machine learning or something?
So you are you are raising, dear Marwi, a very interesting question. We know we work with a very elementary setup, and there are still a lot of manual parts. Okay, if you will, how will the printer identify the faulty part? Is a question that would sort of says, well, we will need sensors, okay? But then, if we need sensors, then we make the printer more complicated, and then it becomes harder to repair itself. And if you will, one of the things that we're thinking about is in the context of, the big logistics chains and chain trouble that we are seeing going on around the world today is, well, what is the simplest set of robots that could achieve self-maintenance collectively? And that links to, again, people saying, well, globalization is a problem. We need to sort of manufacture our own goods, and people talk about like what we call like short circuits, whereby we sort of compactify the things we do within a finite area, or say within a country. And I think that, for example, in Saudi, you see pretty much one extreme situation where much of the country, much of what the country uses is imported. Okay, so and then the question is, okay, so how does what we import able to maintain itself? And then you start thinking, well, maybe there are some parts that we can, maybe there are some repairs we can do ourselves, but maybe there are some repairs we cannot do ourselves. And as a result, we import production capabilities to do these things. And then the question is, how much do we need to import before we declare ourselves independent? Okay, so say we import a manufacturing plant for making circuits. Okay, then we make circuits. That's fine. The circuits can be used to maintain our other industry by replacing old circuits with new circuits, which is fine. Okay, but then how about the manufacturing plant itself? What do we need to do? Do we need to, again, import parts to maintain the manufacturing plant, or do we develop our in-house capability for, in fact, making or repairing the manufacturing plant? And you have this sort of infinite recursive loop that develops, and at some point it has to stop. When do you decide to stop? When do you decide? My thing is pretty much self-sustaining.
Okay, thank you very much, Professor Feron, for this very interesting presentation. So I think we are at a bit of exceeding a bit few minutes, but it's thank you very much for this very nice presentation, Professor Feron. We will hope that we can collaborate with you people in the future. So
with great pleasure.
Yeah, thank you. So now we are going to our next presentations, which is will be presented by Mr. Mohammed Abdul-Hafeez. I believe Mr. Mohammed Abdul-Hafeez is here. So he will talk about pervasive sensing technology for plant digitalizations. So a bit of biography for Mr. Mohammed Abdul-Hafeez. So Mohammed Abdul-Hafeez has 18 years experience in industry, in oil and gas, petrochemical, power and waters, and in many other areas, and he mostly dealing with SCADA, project engineering, and many other things. So he will present this topics from the perspective of his company Emerson. So Mr. Mohammed Hafeez, can you hear us?
Yes, Assalamu alaikum, loud and clear, Mr. Mohammed.
Yes. So if you can share your presentation.
Sure.
And the floor is yours, please.
Thank you so much. Please let me know if you're able to see my screen.
Yes, we can see your screen.
Thank you so much. I would like to first of all apologize. I have some issue on my camera, so I will be not able to show my, a live video, but at least to show my face in a photo, I have just displayed over there. Sorry for that inconvenience. And I would like to say thanks to KFUPM and CIE forum, and also Dr. Muhammad for allowing Emerson to present our technology to the larger forum of KFUPM, and who are going to be the emerging, future, I mean to say, leaders in this technology. Either it may be a product oriented or software oriented or analytics part. And I have seen the other two topics, which was great interest, thanks to the speakers who have delivered that one very well. And let me introduce my, since the introduction by Dr. Muhammad has already done for me, I will not go through that one. Let me just directly go to the topic. So I'm from Emerson. I'm just going to deliver our product solution, which is like a pervasive sensing technology, which will help in plant digitalization, which will be a key pillar for the Industrial Revolution 4.0, which is currently everybody is talking about. Okay, so here is the agenda, what I will follow during the session, and feel free to post your questions so that I can try my level best to answer those while the session is concluded. So I will start with our overview of Emerson digitalization approach. What are the major pillars we do have it? Then followed by the key products, what we have it. When we talk about the key products, that are the data layer, which are like a field sensing devices, which are basically the heart to get more data to the control room to analyze further. Then we will talk about various connectivity tools we have it in terms of different communication protocols, accessing the field instruments back to the control room, delivering the data. Then followed by the asset health monitoring and analytics. That would be a very much interesting topic, where we see that many of the customers are talking about asset machine learning and artificial intelligence that is embedded in some of the assets applications we will talk about, and we will touch base on that part as well. And finally concluding with like the question and answers, which we'll have to address those if you have anything in your mind. Okay, so when we talk about digital transformation, we say that there are some of the recent developments happening either in terms of people's effectiveness or the workers' effectiveness, rather than going with all manual rounds, like routine physical activities going on every 8 hours in the field, collecting the data manually and reporting those, all manual data. From that perspective, how we can enable those into automated system that can really drive the digital transformation. And that is one of the key where we will see that IR4 will play a major role in driving that 360 degrees shift. So this will help the workers in the field to avoid, or even up to an extent reduce, non-routine physical activities. If you see over here, from the gray area to the colorful, like a darker blue, where we can see that more focus will be getting the data with the automated system there, And those automated systems getting the data will be used to further analyze with an expertise level. So that will really help spending more time on doing analysis rather than collecting the data on the field. Then when we talk about the workers effectiveness, we will also look into the production ultimately will hit, or how much in terms of top quartiles we can reach with the production when we are actually going to implement the digitalization approach in the facilities. So this will greatly help again to the production by reducing the overall shutdown times, not going to have any frequent turnarounds or shutdowns, extending those and targeting those shutdowns. These will really help them when we are going to have all those data readily available for analysis and mitigating the risk over the period of time. Okay, so we have categorized into more four major pillars when we talk about digital transformation. One of the key is about the data layer, which is a heart. We say the more data we have it, the more data we can analyze it. The more data we analyze it, the more actionable information or actionable results can be driven on the field. So when we talk about data, we adopt innovative sensing technologies. What is great about innovative sensing technology is that it's all are battery operated, intrinsically safe to change in the field itself in hazardous areas. Again, the other beauty about this innovative sensing technology is a wireless enabled solution. So it's just like a plug and play. You just install it within few minutes and the data will be live to the control room. We will touch base some of the products what we have it in the data layer. Then going back to the connectivity, we do have like a different connectivity tools. If we are talking about widely accepted industrial wireless communication protocols available, like a wireless HART, ISA 100, Wi-Fi. So these are the major communication protocols available, and what are the capacities of each gateways. We will discuss about that one in the next slides. Then followed by analytics and data management. So this is one of the keys where we'll be touching base on some of the software parts, which will really help to say mitigate the risk on the assets, like what is the performance of the assets, what is the health index of the assets, whether it can be compromised in terms of production without going for a shutdown, or whether these can help mitigate and provide a prescriptive kind of maintenance rather than going on the corrective maintenances. Then we have like a service model, which is many of the customers are looking for, like the product as a service or service as a product, basically subscription as a product. So basically we will be owning the solution for like a agreed period of time. We will do the analysis of all the products assets, and we will deliver to you a data with a recommendation. According to that one, the customer can take it further, that whether they need to change the design or do some of the maintenance activities, or how they can optimize. These are the things which will be covered in this kind of service model. As an Emerson, we are very much in field for wireless business, and we are one of the pioneers to start our wireless business almost like 14 years still. Developments are going on with 51 plus wireless products we have it currently, then 19 plus billion operating hours globally we do have it for different networks. Then we also have like almost all the major automation companies system integration successfully done. We have like a proven results and white papers on that, and we are also honored to have like a consecutive 11 years of winning the wireless infrastructure category in the Control Reader's Choice. Then we have like a global expertise available, and few of them are in Middle East and Africa, and two of those are available in Dhahran Techno Valley, which are just a few miles from your offices. Then we have like a 7+ plant operation solutions. When we put all those four major pillars with the products, we can see that we are covering some of the process instrumentation, like pressure gauges which are enabled with wireless, then non-intrusive sensors like a temperature measurement without any insertion, and which can avoid greatly any production isolations or safety to the people getting affected with corrosive environment. Then we do have it the acoustic based, again non-intrusive sensors, which will be used for steam traps or PRVs losses over a period of time, or how much actually we are losing it in terms of production without monitoring those devices or assets. Then we have like a equipment monitoring, like a pump vibration monitoring, or like a corrosion monitoring for the asset integrity. Either it may be inline or non-intrusive kind of solution to a risk to measure the risk and mitigations and also the impacts on the corrosions. Then we will have some of the products which are for the people's safety, to make sure that the people are in the safe area, working in the assigned area, and also to make sure the productivity of the people's and the working hours are being achieved by those products. So we will also touch base on the data connectivity, as I mentioned, some of the health applications. I think we have to cover up and wrap up everything in 45 minutes. Let me try to do it very simple, where we will cover a couple of digitalization solutions, which will help us, in current industry for, utilizing and using there. Okay, so how we can start deploying the digital transformation at your facility? So we always take it as a small steps to make sure that customer is seeing the real benefit of deploying that one. Okay, and after deploying that one, they see the real ROI calculations, like a return of investment or the payback for those small investment, then scale it to the next level. So we also recommend those, like utilizing the phase one with a small scale, as I rightly mentioned, wireless acoustic devices as an example, where you can start with some of the PRV monitoring system or like a steam trap monitoring system with a small scale investment, then see the results as a ROI. Maybe the ROI calculations for your facility can bring a value or a cash back with like a 6 months payback or 1 year payback. According to that one, you can move on the next phase, that is more applications or more asset health monitoring system. Either it may be like a corrosion monitoring or maybe like a process monitoring. Then the third phase will be like, once you have like a multiple assets being monitored with a small scale investment gradually increasing over there, then you can introduce our plant web optics, which can really help you to access multiple assets in your facilities, like heat exchangers, PRV, steam traps, pumps, cooling towers. So this will be like a bird view, okay, for the complete facility, where we stand in terms of overall health of multiple assets in your facility. And that will also let you know that which assets are, overaging, or which assets needs particular attention and all this stuff. So this will be a more focused area for machine learning and artificial intelligence. We will be covering few of that. Slides covering for the plant web insight. That is a basically light tool for that kind of applications. Then followed by that, we have like a various connectivities. Now everybody's talking about cloud services, taking the data back to the cloud, getting it analyzed and recommended by the vendors or by the expertise. This is also possible with our portfolio, what we have it in digital transformation. Okay, so basically Emerson is using wireless HART IEC 62591 standard as a communication protocol, which is widely accepted, and majority of the vendors are using this kind of communication protocol. And this communication protocol is not new to the industry, since HART is there for ages, and we are just using those HART, it's a communication enabled with wireless. That's it. So these can also be used on existing infrastructure, what you have it with wired HART, devices, where we can provide either a thumb adapters, which is like a basically loop powered wireless thumb adapters, which can convert wire to wireless, or strengthen the network with wireless HART in the existing wired HART systems. So when we talk about wireless HART, it's basically a self-organizing and self-healing networks. If you see over here, if there is a obstruction in between, where you see that each device is talking to like a 2 or 3 neighbors, to make sure the reliability is achieved and to make sure that it is self-organizing. And whenever there is a break in the signals, it's also self-healing. If you see over here, when there is a crossing of a truck, moving truck in between the signals, which is well-established network, it will end up with a self-healing and self-organizing network. So it will automatically recapture the network and assign those, data to the nearest neighbor, so that the data can be delivered back to the control room or back to the gateway with a 99.9% reliability. It's very simple to deploy. When we talk about wireless, some of the customers say that it's very tedious. It's not like a rocket science. It's very simple, where we need two of them inputs for each of the field instruments or on the gateway side. So basically, it's talking about the network ID and join key. So it also provides like a whitelisting of the devices, so that the security threats can be avoided, where any intrusions can be possible to have it. And these communication protocols are decoded with 128-bit encryption that is majorly used in the credit cards. And we have written a lot of white papers, proven results on cybersecurity and security of the data to be, in the field. Okay, so since we talked about some of the advantages, we will also see that how the existing facilities can, capitalize on the current, facility install base with the recent developments and capitalize on the existing install base there. So wired process, as I mentioned, are like a more widely accepted with wired hard communications. We can utilize those, infrastructures also with the wireless communications, where all the additional inputs, which are basically for asset health monitoring, like a pump health monitoring, for suction pressure, discharge pressures, or heat exchangers, falling rates, where we need to more focus on the falling rates, that can be also achieved, where currently all manual rounds are effective rather than automating those. So these can be really helping and enabling such kind of data to be delivered with the use of wireless communication. Then the reliability of the network will be greatly achieved, where we will ensure that wireless devices are connected to minimum required neighbors, and the gateways are connected back to the DCS, with overall reduction of IO cards, or the IOs in the which will be basically like a soft IOs. And this will also greatly reduce the complexity of the system. Then finally, we are capable of deploying Wi-Fi network solutions as well, where you might be interested in having like some of the CCTV cameras, mobile worker facilities, to ensure that the process areas are getting continuously monitored. If anybody is in danger, to address that one, or like a fence area monitoring to make sure that someone or the intruder are not entering the area itself. So now we will go to the products overview. We will cover some of the products which are very key in every industry and which are more common in that industry. As I mentioned, we are celebrating like a 14 plus years of wireless launch of our different products, like 51 plus products and analytics softwares. We are proud to say that we have like a many proven results, not only globally, but in very specific in Saudi also. We have like a many install base and footprints in Aramco, SABIC, SEC, SWCC. Then yeah, so what it can really bring the value when we are going to actually deploy the wireless solution. So it will definitely help to avoid the overall total cost of investment. Sorry, like eliminating cost of cablings, reducing the civil works complexity, then accommodating the chain. That means at any time you can introduce any kind of pressure transmitter as an example, or temperature transmitter, without any much modification. So it's very flexible, easy to accommodate any change in the requirements in the field, on the brownfield applications, and also to ensure safety. So that will also increase the safety of like a safety shower monitoring or CCTV monitoring. This will also greatly help like a personal and assets monitoring. Then improve reliability, where we can avoid unmanned outages or also to reduce, manual rounds, which can greatly help in terms of reliability. If you see what so we have categorized basically into two areas. One is for the process monitoring, another for the reliability monitoring. We do have some of the products which is already there in the field, like a wired devices. Yes, the same wired devices can also be supplied with a wireless solution, where might be on the existing facility running a cable for like a n number of meters is very difficult, or maybe to the conjunction of the areas. This can really help to switch over with a wireless solution, where we talk about the pressure in terms of pressure monitoring or temperature monitoring or level or flow, which are basically the key for the process control and advancements in the field area. Then we have like some of the products which are in the reliability monitoring area, where we talk about vibration on the pumps or any vibrating applications like a fin fans, cooling towers. Then we do have it for the acoustic device, as I mentioned, for the flare wall monitoring system or PRV monitoring system. And we do have some of the solutions like a safety shower monitoring. So we will just discuss a little bit on that one. Like majority of the old, say facilities still have like all manually operated, manually inspected safety showers, which can be really automated with using a digital transformation technology. Then we have like a gas monitoring. If you're talking about any toxic gases like S2S or carbon monoxide or oxygen depletion, this can also be able to monitor by these applications. Then location awareness, which I just mentioned about this, that these are the products which will really help the people's effectiveness and productivity on the facilities. Then the corrosion monitoring and the thumb adapters. So this will be like a asset integrity monitoring and enabling the wired devices to the wireless one. So how these devices will communicate? We have certain guidelines as industry practices where each categories are, defined in the design criteria itself, like how much congested the process area is, like if it is a heavy obstructed, like a medium obstruction, light obstruction. We categorize like densely obstructed, like say for example, if it is heavy obstructed, where a small truck cannot move in between those assets. That means that is a heavy obstruction in our terminology. We will make sure that that kind of obstruction will have a wireless communication established with a reliability of 99.9%, where we say that the best recommended practices is that every 30 meters we need to have one device for that kind of heavy obstruction. When we go to the line of sight, where we see that kind of open areas like a tank areas, or where the each transmitter antenna can see the gateway or the neighboring devices without any obstruction, it can go up to 800 meters without any obstruction. So they can talk in between without any repeaters, like 800 meters. Then we do have like a different kinds of antennas to meet the customer requirements, like what kind of design of the antenna to be considered based on the facility classification, like heavy obstructed, less obstructed, no obstruction at all. According to that one, we will choose the different kinds of antennas, which can go in a range of like a high gain antennas with 800 meters up to like a 1.12 kilometers even. So these are the different ranges of products what we have it in terms of antenna for the communication. When we talk about wireless, definitely every customer is looking for the battery life. What is the performance of the battery? How it can help them, to make sure that they are not getting a shortage of those, data without any interruption, to make sure that the data is readily available back to the control room without any obstruction. So the battery performance is always driven by the update rates. If you see over here, the color code, how fast the frequent update rates you need it, according to that one, the battery power consumption will be achieved. So the more the battery consumption, the more the update rates are being used there. So basically, if you're talking about the 1 second update rate to 60 seconds, the battery life can extend from like 2 years to 10 years based on the update rates what we are using here. And this can also give a kind of analytics that like 6 months before or 1 month before, a kind of alert that the battery is completely draining, and you can immediately go for a maintenance or change those batteries, well in time without any shortage of the batteries as a kind of maintenance activities carrying out. Okay, so these are the different products what we have it, like wireless products for pressure monitoring or flow monitoring or DP level monitoring. Then we have it the pressure gauges, some of the pressure gauges which are every couple of weeks being changed, that can be again replaced within like a 3 or 4 years without any interruption to the process. Lot of I mean to say those pressure gauges are being replaced every 2 weeks or 3 weeks or even up to like a 1 month, which are very critical, that can be replaced by these sensors, which are basically lasting for 3 to 5 years minimum. Then we have like in a temperature product portfolio, we have it like a different kinds of clamp on temperature sensors, which can really give a real input, really insight pressure temperature measurement without any intrusion in the pipe or on the tank. Then we do have like a high density temperature measurement, which can accept 4 inputs in the field, and this will greatly help to reduce 4 hardwired IOs in the control room. Okay, now going back to the level measurement, we have like we as an Emerson has launched a guided wave radar and the wireless enabled, which was like almost like a 7 years back, and we as an Emerson are the first to introduce the wireless guided wave radar in the industry, and we have like a huge install base globally for this kind of application and sorry, for this kind of product. Then we have like for the switching level, like a high level alarm, low level alarms with a vibrating fork principle. We are supplying these the tuning forks for alarming level with a wireless enabled solution. Then the acoustic device, which I mentioned, these can be even customized based on the customer requirement that they want to see, where they have like a acoustic noise generations that can be basically captured by this sensor. And basically it also has a temperature, skin temperature measurement. This can help as a raw inputs, taking further that raw input and doing conversions and analyzing that what data can be interpreted by those raw inputs. So many of the customers are coming out of box solution with their own with this kind of solution. Then there are like a totalizers where like a existing facilities, many of the existing facilities do have like a turbine flow meters that are basically they are like a mechanical turbine flow meters. These they want to have like a automated totalizing value to be delivered back to the control room. Yes, it's possible, where we will use the existing turbine flow meters frequency outputs, and we convert those frequency outputs to wireless totalizer, and this will be displayed not only in the field but it can be delivered back to the control room as well. Then the toxic gas, which I just mentioned, that we have like a universal transmitter, which is like a plug and play kind of solution for any kind of sensors. If you are taking like a H2S, O2, CO, LEL is also going to be launched very within like a couple of months. So the same transmitter can be used for multiple sensors based on the customer requirement, and this will greatly help to reduce the inventory for the number of transmitters to one, rather than going with 4 different kind of sub transmitters for 4 different kind of sensors. Safety showers, which are basically for monitoring the level switches, wall position monitoring, safety shower monitoring, and some of the customers are using this for the gate monitoring. So whenever anybody is intruding inside the gate, they will be seeing immediately that somebody entered in the facility. That can be also monitored by this solution. Then thief hatch monitoring, some of them are used for the custody level measurements or custody transfer. These are like a great help for them to avoid such kind of incidents happening on the facilities. Then we have like a corrosion monitoring, as I mentioned, non-intrusive type, which will really help to measure every 12 hours that what is the metal losses or metal thickness losses over a period of time. Then we have like a ER or LPR probes for inline corrosion monitoring that will help to know what is the corrosivity of the process and what are the risks associated with those corrosivities, whether we need to inject more chemicals or we need to balance, the production optimization, or whether we can be able to increase the production or run a conservative production. These are interlinked with those kind of corrosion monitoring system. Then the thumb adapter, which I mentioned, that is like a loop powered thumb adapter, which converts basically wired hard signal to the wireless hard signal. And these can be used with any kind of different products or different vendors. Basically, the requirement is that each device should have like a hard enabled output. Then we have like a vibration, different kinds of vibration solutions for monitoring the vibration and temperature. Then we do have like AMS specs monitoring, which is basically used for configuring the field instruments. So very easy to plug and play and do the configurations, store the data, get the data back to the control room for analysis. Different kinds of batteries are available based on the requirement, based on the scan rates, based on the life, and based on the performance of the how frequently the devices need to be, delivering the data. Pressure needs fast update rates, level might not need, temperature might not need fast update rates because it's a slow moving process variable. So based on that one, customer can pick and choose, or we can recommend them accordingly the batteries for those parameters to be monitored. Let me touch that one in different slide. So we have like a different kinds of corrosion monitoring system. When we talk about the COPANS as an inspection module, where customer wants to have it like a COPANS, getting the data for analysis every 6 months, retrieving that one, doing the analysis in the lab condition. This can be done over there. Then we have it inline non-intrusive, which I mentioned, basically to cover the risk monitoring and also to the impact of those assets, which is getting corroded over a period of time. How the system looks like this. If you see, the wireless hard sensors are scattered either in the pipe area or in the tank area, scattered with the different kinds of principles like inline or a non-intrusive kind of solution. And these data is being delivered to the gateways, nearest gateways, which can accept up to 200 sensors per gateway. And this gateway will communicate to the analytics software, which is a dashboard which takes the raw inputs like a UT thickness as an acoustic noise, plus also the temperature, and that raw inputs are correlated and converted into an actionable information. Okay, so these are the different kinds of sensors what we have it for corrosion monitoring. The corrosion monitoring can also be achieved without removing any coating on the pipe or on the tank. This will also greatly help to avoid the galvanized corrosion happening. So this can be just like a magnetically coupled, which is sitting on the pipe or on the tank without any intrusion, without any modification of the pipe. And this can go up to 600 degrees Celsius without any interruption in the performance of the devices over there. And the battery life for these devices are up to 9 years, and it can be used in class 1 D1 zone 0 based on the requirements on the field. We do have like a ROI calculations based on the applications, where we provide to the customer that if they are deploying an HF alkylation or sour water stripper, they can see that how many sensors need to be deployed, and according to number of sensors going to be deployed, what is the value of that investment, and with those investment, what is the payback period. If you see as an example of crude and vacuum pipe application, you can see that there is only 1 month payback with those kind of investments on like number of sensors and dollar value. So you can see that a very quick ROIs are being achieved for those kind of investments, and that is justifiable for immediate deployment of like this kind of application in the facility. When we see about the maintenance activities for the wireless products, it's very modular, where you can plug and play with the different kinds of batteries, different kinds of enclosures, even different kinds of transmitters over there. So this can greatly help to avoid, or I can say reduce number of sensors or number of transmitters in the inventory, rather than going with all different types of typical transmitters as space in the facility. So this will greatly help to minimize the inventory overall. So these are the different kinds of gateways or the connectivity tools. We do have it in Emerson. So we have like a gateways which are capable of 25 devices minimum to 200 devices currently. And these gateways are basically wireless HART enabled communication protocol used. Then we do have it wireless HART and ISA also, if you require, like you have like in the facility different kinds of ISA products, Yes, we can provide a gateway with 2 communication protocols, or even up to 3 communication protocols, like a 3-in-1. Basically, we can provide you wireless HART, ISA 100, and also the Wi-Fi based solution. Then we have recently launched these DIN rail mounted gateways, which can go to up to 200 devices. And we have also various communication protocols like a Modbus, OPC-DA, then OPC-UA also launched recently. These are being widely used in Saudi Arabia customers' sites as well. So this is a gateway which we recently launched with a joint venture with Cisco. So basically, we are using Cisco gateways for Wi-Fi solution and our gateways for wireless HART. So it will be used as a backhaul system for the CCTVs as an example, or for the Wi-Fi based solutions, and for the process instruments with wireless HART gateway. So this will also help like gateways deployment on the field with a different kind of backbones, like either if you want to go with a wireless HART or Wi-Fi based gateways to lay the backbone for wireless infrastructure, then build on that, and based on that the requirement, you can plug and play the field instruments according to the backbone what you have already developed in the facility. So we have like a various connectivity tools. If you're talking about a standalone system, or taking into the DCS, or taking to the next layer like a 2.53 layer 4, where you want to have like all the analytics part sitting on that kind of platforms, it will greatly help to get the data wherever you want to take it. So this is some of the typical examples what we do have it, various connectivity tools. And as I mentioned, we have like a different communication connectors, protocols, I can say, used, which are basically to fulfill the requirement of host DCS or SCADA system, where these softwares can be plugged and easily available, those inputs to the DCS for visualization. And we have like a assets health monitoring. We will just going to cover a few of the slides on the asset health. Basically, we have like a 12+ asset health monitoring with the help of artificial intelligence and machine learning. We have like a software packed with steam traps, pumps, location, heat exchangers, inline corrosion, to name a few, and then also the network management, cooling towers, and pressure relief valves. So we will cover a few of them in the next slides. We are running short of time. I will just try to cope up on these. These are the last slides for the asset health. Okay, so when we talk about the steam traps are basically like a mechanical steam traps, right? So mechanical devices. Basically, nothing is being monitored currently in the industry, and these are like a reactive based of approach. Like every 3 years or 2 years, customer do a third-party inspection, and they carry out those, feedback as an activities for corrective maintenance over a period of time for the next 2 years. So this is greatly compromising on the production, like in terms of steam production and efficiency of the boiler, and also the safety of the turbines, which is greatly being compromised. So what we have a solution is that we provide a non-intrusive, like a simply clamp on strap with the acoustic device on the steam trap upstream side. This will be really this will be monitoring in a real time 24/7 the active events captured by the steam trap, whether it's going in like a cold condition, blow through condition. And this will really help, okay, to know that whether we are losing a great amount of energy through this blow through condition, where steam getting generated from boilers are getting lost by the steam traps, or loss of emissions, like because these kind of emissions are can be avoided once we have like immediate reporting of those bad actors like steam traps, either compromising the steam quality in terms of condensate or blow through conditions, where we are losing the steam out of the steam trap device itself. So this will help to repair or replace steam traps well in time, immediately, without any time to wait for like every 2 years. Rather than that one, it can be achieved immediately. And 80% of the steam being say generated by the boilers up to the 20% of that is being lost due to these steam traps, bad actors itself. So these can be greatly helping to avoid such kind of incidents, and which can help to retrieve those steam losses and avoid those emissions. Then we have like a pipe integrity, where we talk about the corrosion monitoring, which will help the pipe integrity and asset integrity. Also the corrosion rates, which are greatly helping us to make sure that we are having like a targeted shutdowns or event reconfiguration, so that that can help to target the shutdowns for that facility or that point itself. So the PRV again is a mechanical device. This will be also monitored with this acoustic device, which will capture the events, and this will help to avoid the production losses, and which is going to the flare, which is indirectly you are burning your production. So these can help to avoid such kind of incidents, like a PRV is getting leaks, okay, and the production is getting lost over this in terms of burning. So these can be greatly helped, and we have some of the economic models which can give you a kind of production losses analysis, which can be avoided with this kind of implementation. The payback, you can see like it can be varying from like a 2 months to 1 year, based on the deployment and based on the criticality of the PRVs. Then on the heat exchangers, majority of the customers are doing a kind of practices where they fetch the data from the heat exchangers into an Excel sheet. They do have like a offline calculations for overall health monitoring of the heat exchangers. Currently, with this deployment of automated system like analytics software, these can greatly help them getting this done automated one, like a real time. Every couple of minutes, these data is fetched into the this software to do the analysis and let us know that where exactly the problem is and what is the status of this heat exchanger and how it can be avoided by having like a predictive maintenance with these inputs. Then if you see the analysis like a ROI calculations, that how much annual losses can be recovered for such kind of heat exchanger. This is one of the typical examples showing from a typical refinery of 200 barrels per day. Then if you go to the air-cooled heat exchanger, the similar fashion, where we can see the detector, where we can see the detection of exchanger falling rate and also the limit column flaring. So this will also help us to know the operational benefits and maintenance benefits, and also the optimization of those kind of deployments with this software part, which can greatly help in analyzing such kind of data. Then the pumps, as you see, these are like many of the pumps are non-essential, mechanical, which are not being monitored, and for those operators are keep on running the facility, and this can be automated with such kind of inputs, which basically can be gathered in this software, and this can further analyze the overall health index of the pumps, which can greatly be achieved by knowing the suction pressure, discharge pressure, or the strainer getting I mean to say filter across the strainer is also getting plugged. So these kind of inputs can greatly help in avoiding such kind of incidents, like a dry run of the pumps or overrunning of the pumps. These can be really avoided by monitoring such kind of assets. Inline corrosion, which I have just discussed on that one. This is one of the applications for safety monitoring of the people. Basically, these are the personal tags which are wearable by the employees, which are the contractors or the visitors in the facility. So this will greatly help day-to-day activities in the facility, being getting real-time live monitoring of the personnel in the facility, whether they are assigned in the facility for such kind of job, will be real-time monitored every minute to make sure that the people, those who are assigned to that area, are in the right area and safe area or not. And this will also help to know the geofencing, like if anybody intruders in that particular area, this can be giving you alert that someone with this assigned area is supposed to be in the area B, but he entered in area A. So immediately the emergency responder can guide him that you are not supposed to be here, and to avoid such kind of incidents happening there. And this can also help in safety mustering, either in it may be in terms of safety drills or in during the actual emergencies happening over there. to make sure the people get evacuated from the area to the nearest safety mustering, so that this can greatly help again to avoid lost time injuries. And it can be used by the safety department to show that how much how much lost time lost time injuries are being avoided by monitoring and implementing such kind of mechanism in the facility. And another one is about the safety alert. If someone needs any help, there is a push button in this kind of device where they can push that one, and immediately the control room will get an alert that someone needs an emergency help, so that the emergency responder can go and help him to evacuate that area. When we have like a large deployments with multiple gateways and multiple devices over there, definitely such a kind of networks need to be maintained. And we do have a software again to maintain and manage such kind of networks, which can help you to know that which gateways are overloaded, which gateways need to be considered as if as a secondary one or primary one. Based on the update rates, it can automatically manipulate and advise you to balance the network capacities. And also for the power modules, to make sure that how much say batteries are having a life remaining for like another 3 months, 6 months. According to that one, you can plan for the preventive maintenance, and also to make sure that you have a right inventory in place to do the replacements. So when we see as a complete portfolio, yes, we have from the data layer like a field sensing devices, either to pressure, temperature, acoustic devices, to the software part, which helps to monitor those kind of assets. And from that assets, which can be taken to the multiple assets like a plant of optics. And these can be taken further to, workflow integration, creating a kind of corrective maintenance jobs, preventive maintenance jobs, or taking to the data layer, to the cloud level, to be easily accessible to the plant areas or to the higher management to access where we stand overall in terms of performance of our assets in the facility. That's it. I think I'm on time. I'm really sorry that I was super fast to cover some of those slides. Thank you so much, and let me know if you have any questions. I will try my level best to answer those questions.
Thank you, Mr. Mohammed Hafeez, for a very interesting presentation. So we can have like maybe 1 or 2 questions from the audience. Please. While we are waiting for the question from the audience, so I would like to ask a question whether this type of like new sensors with this wireless communication is suitable for area classified as area that contain explosive gas or something.
Yes, you are absolutely right. These are classified to use in zone 0, zone 1, area classified, IP68 rated, and intrinsically safe. And these can be field replaceable with the batteries over there. Yes.
Okay, thank you. So we have another question from Mr. Danis Muazzam. So he asked about a pull interval of the device and effect on battery effect. Can they be used in high-speed data polling areas?
Okay, that's a great question. Yeah, so it all depends upon how fast the update is required. As we see, like a pressure transmitter or flow transmitters, these are like a fast moving variables, right? So that definitely needs a fast update or scanning rate for those kind of parameters. When we see on the other end, like a level measurement or temperature measurement, these are like a slow moving process variable. So that can be compromised with the higher scan rates. And the limitations currently, not only on Emerson products, but on the wireless technology itself, is that currently the minimum scan rate for each device is 1 second. So below than that 1 second, still the developments are going on, but as a official commercially available, no such kind of devices are available. But if you go with the 1 second minimum, it can take a battery life consumption up to 2 years. And if you go for the slow scan rates, like a 16 seconds or 4 seconds, the battery life will be extended with additional like 2 years, like 4 to 6 years. Hope I answered your question.
Okay, thank you. Is there any more question for Mr. Mohammed Hafeez?
Any more questions to Dr. Mohammed?
Yeah, so we have another question from Mr. Hussein Al-Juman. He asked about, do you use edge computing for any of your applications?
Yeah, very good question. Yes, we are using some of the edge computing solutions from our systems and reliability. It is customizable based on the requirement of the customer. Yes, we do. We use edge computing as well.
Right. Okay. So is there any more question? Maybe the last question for Mr. Mohammed Hafeez. Yes, Mr. Ali Al-Waini.
Assalamu alaikum.
Hello.
I just want to ask about the wireless transmitter. I remember when I work inside the plants, usually there is some problems in compatibilities when you already have a plant, a running plant, and you want to make, for example, an upgrade for a system or to expand the system. Is there more, what causes these, problems between the old system and the new systems? Is there a problem in compatibility usually, or this is just because of the plant commission issues? That's my question.
Okay, great question, sir. Thanks for bringing this one. Yeah, definitely this is one of the challenges where we see while executing on the existing facilities where the connectivity tools are either being rightly used or not. So basically it's about the interoperability, okay, and right tools available in the existing sites. Let's say for example like a Modbus, every DCS as an example, majority of DCS are using like a Modbus communication from those kind of gateways. So if we are able to provide the right Modbus registers for each variable in the field, definitely there shouldn't be an issue at all. But it's a matter of connectors, which we are rightly placing over there to get those data readily available in the format which is basically accepted by the host system. So this is one thing. And the other thing is that either it may be due to some of the obstructions if you're talking about the field instruments or field devices, like electromagnetic effects there, to make sure the best practices are followed so that the network connectivity is achieved, the reliability is achieved on the field network as well. But on the control room side, yes, various connectivity tools are there. That it all depends upon the compatibility and also the cadence of the professional people who are actually going to execute. But almost all the connectivity tools are available. Either it may be from Emerson or from any other vendors. Yes, those kind of things can be achieved. Only the thing is that we need to place the right tools in the right format to get the data delivered back to the host system.
Okay, thank you very much, Mr. Mohammed Hafeez, for this presentation and answering these questions. We thank you for your presentation. So so with this presentation finished, we have completed 3 presentations so far. So we will have a break until 12:30, and then in 12:30 we have another presenter, Mr. Mohammed Al-Halafi from Nozomi Network, where he will talk about securing the industrial control system in the extending edge of IR 4.0. So until then, see you again. Okay.
Okay. So let's start this the second part of our forum. I am Nizar Yazidi from Control and Instrumentation Department. In the second part of our event, we have 3 presentations. The first one will be delivered by Engineer Mohammed Hafeez. and followed by Dr. Solomon AlMadi, and then we have also Dr. Abdullah Al-Halafi.
Thank you.
Let's go now again to the second presentation. The second presentation will be developed by Dr. Solomon AlMadi. I am glad here or so excited to introduce Dr. Solomon AlMadi. Are you here, Dr. Solomon?
Yes, I am here. Thank you.
Okay. MashaAllah, Dr. Solomon has a very large bio. I will introduce something about him. So the topic today will be industrial control system security protection. And Dr. Solomon, he is currently professional engineering senior consultant in process control systems and digital transmission program in Saudi Aramco. He holds a PhD in simulation and computing from Brunel University, UK. Master degree in electric engineering from Southern Methodist University, UK, US, and BS degree in electrical engineering from University of Texas. And he published several papers in IE and ISA. And he is a board member of ISA and International Society of Automation, and also active member in ISA standard and development and reviews. The floor is yours, Dr. Solomon. You're welcome.
Okay, assalamu alaikum and good afternoon, everyone. I hope I am audible. I guess the answer is yes. Okay, fantastic. I would like first to extend my sincere thanks and appreciation to KFUPM for giving me the opportunity to share with you a very important subject that's really impacting everyone's living, whether it's at the personal level, industrial level. Today's my talk is going to be focused on the industrial control system, cybersecurity threats and protection. And by the way, this field is so huge that I only just selected synopsis to give first our students and participants who are here from different diverse backgrounds, first an overview of an ICS system. Then I will be touching base on cyber attacks and strategies for protecting existing ICS systems, summary and potential future opportunities that can be considered by everyone. So one more time, the motivation here is to share with you the landscape from threats and protection, and with the primary focus, and I'm hoping that it will develop the interest with our students at the undergraduate level to specialize in cybersecurity, and for also the graduate level to explore opportunities of research and development and innovation. To begin with, we all know that what is an information system, but here just to baseline, since I'm not sure the different backgrounds of the participants. Whenever we are hearing the terms information system, it is simply the hardware and the software and the people, data procedures that simply used to process information, store it, and make it available for end users for organizational and operational efficiency. And when we talk about an industrial control system, it is the same as an ICS, with the exception that we have instrumentation layer that's basically capture very important information, vital signs of our processes, whether it's a petrochemical or smart grid in the electrical, utilities, and what have you. And on the top of that, we have the advanced logic controller that simply provide monitoring and control strategies for plant operation. And whenever we talk about the process control system, we're simply talking about here a system that supports control and monitor of a process facility or an equipment. It's simply composed of sensors, instrumentations, logic solvers, and with the capability to integrate to the enterprise systems. And there are different types of these different ICS systems, whether it's a basic process control system, you will hear the distributed control system, a DCS, supervisory control, or auxiliary systems. We also have the safety instrumented systems that are typically used as a last resort in ensuring that we have a safe operation in our plant facilities, providing an emergency shutdown systems and or maybe managing the process. Finally, we have the industrial Internet of Things, which has been introduced not too long ago, started back in 2015 with the WEF, the World Economic Forum, with the introduction of the digital transformation, Industrial Revolution 4.0, simply capitalizing on the computing power, the integrated chip, as well as advanced applications where we have extended reachability to enable a new application, whether in the industrial side and or in the enterprise and or I would say civil type support type applications. Now the ICS anatomy, it's very much based on a layer architecture. We have the instrumentation layer, controller, and we have the telecontrol. The point I'm trying to show here, the complexity and the fact that there are some unique protocols that are being implemented at the ICS level that you would not see in the IT domain, which we will highlight the challenges that goes with that in upcoming slides. There's always talks about IoT versus industrial Internet of Things. To us, the only difference here from an application. On the IT side, it's basically focusing on transformative type application in the health, smart cities, government, and what have you. However, in the industrial, is simply focus on manufacturing, oil and gas, utilities, and what have you. And of course, to make all of these different systems, whether it's a basic control systems and or safety system and or an IoT, you will need the communication links, which can be radio, wireless, VSAT. And with that, you are simply expanding your cybersecurity threat vectors. Of course, the nodes, which you use to interconnect all of these different ICS components, can be classical as what you see in the IT world, switches, hubs, routers, firewalls. However, you will see that some of them, they have a little bit of more enabled capabilities that are toward the industrial protocols. Now I gave everyone a level set on what we will be talking about. I would like to move into the next part of my presentation, which is sharing with you the industrial control systems cyber attacks. In general, the primary objective of cybersecurity, whether it's on the enterprise and or in the industrial domain, it's simply to basically deliver on the promise of making sure we have high level of integrity, availability, and confidentiality. Confidentiality relates to data, integrity relates to basically the measured data and what have you, and the content, and the availability is the uptime. And these three different principles are applied on data in general, whether it's at rest, meaning in storage devices or in the memory of the computer chip, and or transient throughout the network as it is going between source to sink. And finally, in use. And in use here, whenever the end user accessing that data, and or maybe the instrument is accessing the data and or capturing the data. And there is a distinction between the information system and the information control systems from the priority order. In the information system, confidentiality is considered the highest, while in the ICS, availability is the highest. And simply because of the operational aspects. It's very important to us to have the plant running, so availability becomes much more crucial to sustain productivity and uptimes. While in the IT domain, confidentiality is more because of how the data being simply shared, transported across different networks and what have you. So that's the priority order, and accordingly, technologies are being adopted or enabled in the IS and the ICS in a different ways to ensure we can deliver on the promise, which is protecting the data from these three attributes. Now, the term that you may hear over time is advanced persistent attacks, because there are different types of attacks. But what we are referencing to whenever we're talking about cybersecurity threats is when there are combined different means that are utilized to penetrate a system and simply inflict a malicious action that will impact the performance of it, resulting in an operation that is simply not reliable and or maybe a major damage. And typically speaking, APTs, they go through three different stages. One is identifications of and selections which target to be hit. And then the hackers will elect and select the soft entry point, delivering a means. It could be a weaponized malware via different approach, phishing email, and or maybe a man in the middle, and or maybe even a compromised chip that's being embedded on the actual motherboard during the hardware delivery from a manufacturer to an end user. The point here, these hackers are very clever, and we as intellectual community who are having the responsibility to ensure we protect our industry, as well as that we have the responsibility to research and innovate, we have to be always ahead of the curve. It is like a Formula One race, and we are head to head with the hackers. The final stage the hacker will do is, once they are succeeding, simply they will exploit the system. And once they do that, that's when hell break loose, resulting in a disaster. Now let's talk about service attacks. Simply, service attacks are considered to be all different points that a hacker may be able to compromise. It can include the cybersecurity measures that you have in place. Because believe it or not, okay, some of the most advanced solutions in cybersecurity have their own vulnerabilities. In fact, whenever there is a patch being delivered to address a malware, by the time that patch is delivered by Microsoft, you will find the hackers are doing reverse engineering on that patch simply to identify what really caused the vulnerability that they are trying to address, and simply come up with an alternate way to re-engineer that vulnerability and or come up with a counter vulnerability to the solution that's being deployed as part of the patch. So the fact that we have a cybersecurity solution does not mean that we are immune. Now, the attack vectors simply encompasses from the actual ICS components and means that are used to address the ICS components. USBs, ports, networks, how it's configured, the telecontrol protocols, the application that's running on it, and actually even the people who are managing these ICSs. And let's not forget the suppliers, because the supply chain goes through different levels and may also invite the participation of more than one supplier in the actual product being delivered to the end user. And that really make the risk much, much higher. One thing in APTs is the fact that once we have a compromise and the attacker created damage, there may be something called secondary attack. It's the him and ah concept. We get hit, and maybe that's when all of our defenses trying to go ahead and address that hit, and all of a sudden there is another wave of hits somewhere else, where the primary one is a distraction, and the major one is a subsequent. And or maybe the compromise itself and the virus that they are having is having the capability to immutate as it goes from one cycle to another. And maybe it is based on a time bomb that simply goes into different formation with time. So for example, if we speaking about malwares as a malicious software, which is considered to be one of the most dangerous means of attacks, there are 12 different forms of malicious softwares, quote unquote malwares, that goes from ransomware, encrypting the hard drive or the data, to actual viruses corrupting your data, wiping some of the data, to worms, to simply a Trojan where it enable an access, fileless type malwares, cryptojack type malwares, making use of your resources to serve somebody else's crypto mining, for example. Okay, botnet type malwares, and the list goes on. The point here is each one of those vulnerability and challenge that these malwares cause, if we want to cover it in detail, honestly speaking, we can spend half a day just talking about ransomware. So this is just a snapshot to tell you that out there, these are the different types of malwares, and I will leave it for you to dig more. One thing that is common among all is they have the ability to simply propagate as they succeed in entering into a system. Equally important, they have the ability to be executed remotely or self-executed, whether when you boot up the system that you are using, because some of them based on boot up, some of them based on maybe a time stamp. And believe it or not, some of them tied up to an actual application that you may be using, directly connected to maybe an Adobe application that you open. So you are using your computer safely and happily, all the applications and data is there, and you click on an application and it may trigger a certain type of a malware. Our ICS layer is equally in danger as much as the computers that are used to manage them. So for example, the RTUs and or the PLCs can go through a process of being infected at the firmware level and or at the logic solver level, altering the information from a data integrity. So for example, if you have a sensor where you have a process that has basically a boiler reflecting the incorrect heat and temperature, may result in overshooting in the heat and or maybe undershooting in the heat, resulting in a process issue. For example, we know silver to be produced require heating. Imagine if the control system reflecting basically a temperature that is much below the threshold of the heat level that the silver line is working on. What's going to happen immediately, that silver will freeze and become solid. And when that happens, it triggers a major disaster for the plant. It may even result in rupturing those soft points in the piping system. And or for you to go ahead and clear it out through the piping, it requires special petrochemical processes and time. So the operation itself now is really impacted and could be impacted for some time. What you see here is roughly 20 top attacks that has been demonstrated and inflicted in our domain. Is this all what we have out there? I'm sure there is much more. Just in 2020-21, these are the major attacks. So our ICS is under the gun in a continuous way. Now we understand the fact that we live in an environment where the probability of a cybersecurity threat is highly unlikely to happen in the industrial domain, as opposed to the old thinking process that, hey, ICS systems are somewhat isolated, and or maybe they are using proprietary protocol. The fact that we have transformed the ICS systems to be based on open protocols, and the fact that we need these ICSs system to be connected to the enterprise invites a lot of risks, but great opportunities for us. Risk from cybersecurity, opportunities from increasing the plant operation and productivity. So if you look at the left-hand side, in line with the Purdue model, there are 4 levels that we typically address from a system perspective. In today's environment, more and more, we see the ICS system to be interoperable, open protocols, and the fact that we have, quote unquote, Ethernet extended all the way down to the lowest layer. In fact, you will hear the term sensor to the cloud. Imagine. So it's from the sensor all the way to the cloud. It is IP, internet. And with all the blessing that IP and Ethernet brings to us, the challenge here, cybersecurity. So what would be our answer on protecting an ICS system? The fundamental answer is, how can I make it more challenging for the hacker to be able to go from one layer to another? So the concept of defense in depth is typically embraced by the end user. In fact, the international standards is built around the same theme, is how can we add different layers to ensure that our system is protected from the physical process, the applications, the computing devices, the network, the perimeters, the physical security, the entry to the ICS system room, and last but not least, in my opinion, the most important one of all is the human being, organization and human aspects. I'll try to elaborate more. So to address these different layers, we have to be systematic in how we address our service of attack and the different cybersecurity vectors that we have in our system. And the fundamental approach is simply to come up with a general diagram of possible attacks, looking at every one specific. So do not look at it, the overall as a holistic, because if you do that, you may overlook some of the specifics. And keep in mind, whatever mitigation we have, it has to be layered. The good news, we have international standards today that can help us out as a great reference. ISO 27005, as well as IEC 62443. I'm just going to share with you here a quick example. On the right-hand side, the vulnerabilities that we are concerned about, somebody modify a SCADA system, for example, or a PLC, and or the HMI. And to get there, we have to deliver a malware, a malicious code that does simply inflict that change. If I go to the left-hand side from a data flow diagram, the attacker has to go through these different entry points to get there. So they may get there through a vulnerability through an actual secure system, a firewall, because the policy is not really stringent, and or there is a vulnerability on the actual firewall itself from a software programming and development. Because as you know it, the secure life cycle, if it's not implemented on a hardware and or a software, that really invites a lot of possibilities regarding entry points to that system being developed. On the network side, whether it's network wireless or wired, it all depends on the protections, the encryptions that's being implemented. I always say that a VPN is an excellent secure solution to provide encryption and protect the data, but it's an awesome delivery of a virus to a network if the VPN borders are compromised. So in essence, these are the different ways that they can compromise and enter to our network. Oh, let's not forget about phishing emails, because with that we can get credentials. These credentials can be used to overcome the wireless network and have somebody who is not authorized access that network. Or maybe utilizing a brute force type of attack. And now with the computing power, the attackers, if you are using a password that is not complex, it may take them hours before they break into your system password. Assuming that they got into our network, then it becomes now easy ride, where they'll be able to make it all the way to the PLC. To ensure that we are addressing these different quote unquote opportunities that we are giving away to the hacker, we as professionals who are addressing cybersecurity go through a process called risk assessment, where we identify the risk and we go through a systematic way we're evaluating it, whether it is technical, organizational, and maybe even process. And once we identify these risks and we evaluate them, we come up with risk treatment plans. And like I mentioned earlier, there are international standards that does that. Equally important, there are many tools, automation tools that you can make use of, that you can build the profile of the network on these risk assessment tools, which would help us to better document and simply give us an effective way of keeping track of these risks and the mitigation controls. Once all done and said, then we will have to accept the risk, because we have to run the operation. Of course, we accept risk when they are low. In other words, because of cybersecurity, we cannot stop. Our objective here is to minimize the likelihood of a vulnerability, and if we get caught by a vulnerability, how responsive we are in discovering it. And Mazomi speakers, Mr. Mohammed, he talked about the anomaly detection, which is one of the technologies that used to simply give us the early indicators of behaviors that are not desirable from a cybersecurity. And once these behaviors are triggered, then it will drive some subsequent processes within the organization to simply go after and rescue the hardware in question. So to summarize, in the risk reduction, it's all about defense in depth. It covers all the attributes from computing, networking, physical, organizational, utilizing technologies, whether we're talking about firewalling, network segmentation, zoning, encryptions, the use of operating systems that are well configured, protected, and of course, let's not forget the access controls and encrypting the data. So from an architecture perspective, to better provide protections, a DMZ, a demilitarized zone, is typically speaking adopted simply to give a buffer between us and the outside world. Zoning is used as another approach to provide segmentations, and of course, the cybersecurity solution, whether it is the antivirus, whitelisting, compliance tools, and what have you. If we just take a deeper look here, the plant's layers from level 0 to the enterprise, the idea here is for only one system is we create a zone that, ultimately speaking, protected by a firewall, where the cybersecurity solutions are there to simply utilize to keeping the system up to date. And of course, the DMZ is considered as a buffer. And finally, when we connect to the outside world, we will have to have basically the level of protections. A firewall, a data diode, intrusion prevention systems. I always say that, you know, buying a cybersecurity solution is just like going to the mall to buy a shirt. There are so many of them out there. But to the end user, you have to really pick and select the one fits your system and make sure that it is addressed and configured the best way to meet the business objective of facilitating the data from the lowest level to the highest level. I always say that cybersecurity is not a hurdle. It is all about enabling the business. Without cybersecurity, we cannot enable the business. As a strategies for zoning, we typically speaking look at functionalities that are of the same. We put them together as a group, and or facilities. We based on geographical areas and what have you. So similar security requirements are put together in a zone. So for example, if we have remote access, will be on a unique zone. Wireless infrastructure will be on a unique zone. And when we do this, we simply allow only the traffic that's supposed to be going from point A to point B. So for example, in the safety system here, if I want to go ahead and connect it to the control system, I simply establish a secure conduit that is basically part of this zone, which is encompassed in the bigger zone of the PCS layer. So you can have subzones into a security zone if you wish to do so. But let's just not be carried out with having a lot of subzones, because when you do that, it becomes more complex. So I always say that make sure the selections of these zones fit the actual purpose that we started with, which is enabling the business capabilities for our plant operation. And of course, if we're talking about a huge deployment where we have multiple systems, a safety, a basic, a SCADA, an enterprise, we can have each one of them in a unique zone with the bells and whistles of protections, so we can safely exchange data. Now, zoning and architecturally design the cybersecurity is covered extensively and IEC 62443. And what you see here in the standard, it's built in a unique way where it starts with all the requirements from an end user, system integrator, and then manufacturer, and delivering on the solution in a cyberly secured fashion from the component level all the way up to the system level. So as a reference, especially if you are in the college universities, you simply can capitalize on IEC 62443 by joining the International Society of Automation. The membership is almost like $10, which is about 40 riyals, but it gives you access to this rich standard. There is an overlap, and I always call it as an integration between IEC and the NIST cybersecurity framework, which is typically focused on five main domains: identify, protect, detect, respond, recover. And what you see here is the different solutions from a cybersecurity that we can buy. Remember we said, if you go to the mall, you can get all of these different services. Same thing. Asset management for asset inventory, because if you do not have an asset management for your ICS system, you simply cannot keep track of the asset from an access control, logs, inventory. Even if you want to do a risk assessment, if you don't have a credible asset management or database, you may overlook an asset. And when you do so, you will be overlooking deploying a control. And when you do so, you're simply inviting troubles to the plant operation. So this framework gives us the opportunity to ensure from a cybersecurity, we are addressing the different technologies and best practices in all different layers. Now, I started by saying that the hackers get clever every day. We are almost like in a formula race every day. And the minute that we have addressed a vulnerability, another one service. That's why cybersecurity is a continuous improvement. In the industrial domain and even in the IT domain. But in the industrial domain, it's really important simply because of the impact. God forbid, we have a ransomware that compromises a plant, then all the workstations and the servers are encrypted. We do not have the encryption key. We do not have access to the control system. Then now the plant is running blindly. And when that happens, guess what would be the response? It will be shutting down the plant. And to shut the plant abruptly is not an easy task. So our objective here is simply not to get there and to avoid maybe more catastrophic type events where someone alters the programmable logic controllers, logic itself, with deception resulting in electromechanical major disaster that result in a spill or an explosion. So a risk management is always has to be up to date in our operation, identifying the risk, coming up with the protection, and it is a process that is continuous. We plan them, then we go ahead and implement them, and then we check our effectiveness. And if there is areas of improvement, we act to improve them again. Then we go through that process over and over. Of course, to do all of this wonderful work, we need skilled workforce. The skilled workforce, you in academia, it's favorable that beside you paying attention in your coursework is to put under your belt certifications in the cybersecurity domain. And there's so many of them out there. So when you are done with your bachelor degree, you'll be much more valuable to the industry. And of course, for our graduate students, we have amazing opportunities in identifying risks, how we protect, detect, respond, and recover. The use of machine learning. Because right now, we do have the ability to be a little bit, I would say, head to head with the hacker as they are attacking us on a honeypot. We can understand the behavior of attack. And through machine learning, we can learn what they are doing and do reverse engineering and be able to go ahead and in a speedy way have the risk mitigation. And that's the power of the machine learning and the data analytics, which is byproducts of Industrial Revolution 4.0, but academia, the lion's share of contribution is coming from academia in this domain, believe it or not. Of course, the hardware, whether we're talking about here secured chips, secure by design, the operating system, how we inflict more cybersecurity hooks in the actual operating system, so when we connect to the application itself, the application is more secure. So these are wonderful opportunities that can be explored from a research perspective. With this, I would like to thank you very much for listening, and I would like to leave the rest of the time for questions.
Okay, thank you very much, Dr. Salman, for this nice presentation. And now I will open the floor for audience to have a question. Already we have one question from Masoud Al-Anazi. Do the subzones cause some latency?
Sure. Latency is one of the key considerations you have to simply consider in the end-to-end design of a cybersecurity solution. Whenever you are introducing a firewall, an AVS, antivirus, because AVS, they have their own scan time. And there's something called host intrusion detection systems or host intrusion prevention systems. Those, typically speaking, they eat up some of the CPU time of your node. So if you are talking about robotic, every millisecond matters. That's why zoning is not favored for hard real-time systems. Quote unquote, we call them deterministic systems. However, for process automation, petrochemicals, utilities, and most of the power applications, we can tolerate a delay that the industrial grade systems that are available today can be utilized without impacting the time delay. One point that I must highlight is whenever you are doing the design and having these conduits and or layers, there has to be some kind of a holistic assessment on the end-to-end system performance. While we may be able to do it through simulation, the real test is when you have it implemented. So thank you for the question. That definitely has to be considered as part of the design. Thank you.
Okay, thank you very much, Dr. Salman. We have another question. You mentioned the machine learning for their ability to detect the cyber. How about settling or steal attackers from control point of view?
Well, stealth attacks, I think that's what you meant. Okay?
Yes, stealth, yeah.
Yeah, stealth attack is all attacks are in a way are stealth in nature, at the beginning unless they are using a vulnerability that is known, quote unquote. We know the signature of attack. So if you have an operation that is up to date with the latest bells and whistles of antivirus, malware protections, whitelistings, your intrusion prevention system is up to date, those will be detected and stop right there. Our fear is the stealth, or quote unquote, we call them in the industry zero-day attacks. Now, the zero-day attacks, there are different means of discovering them. As a zero-day attack, they inflict some behavioral changes, whether at the network level and or at the application level. So you may see an intense traffic increase, and or maybe the relationship of communication now all of a sudden has changed. We know, for example, process A communicate to process B, but all of a sudden now process A is connected to 50 other devices that are outside the zone of process B. And that's where the power of, I would say, anomaly detections and or what we call them real-time monitoring, event monitoring, can help us out to detect these type of changes in behavior. I must add also, in the industry, the whitelisting capability. If there is any changes in the behavior of a system, it should trigger an event. So combining anomaly detections with the host-based level type protection, we should be able to detect it. However, wonderful, we detected it, but it may be too late for us to protect, meaning that a ransomware was enabled or activated. The last log showed that, hey, my whitelisting indicate that an application was triggered, created an event, and that was the last good value that I know. After that, it was encrypted, and I have no access to it. 0 day is 0 day, meaning that we got hit. And that's where we have to have other layers of defense, something called incident response plan, where it put together the systematic approach to simply unlock that machine that was compromised and either deploy another machine or somehow cleanse that machine that got compromised so we can sustain the operation. I hope I answered your question. Next.
Thank you, Dr. Salman, for this clear answer. We have another question from Mohammed Al-Hassan. He raising his hand. Mohammed Hassan, you have a question. Okay, Ali Al-Awami, do you have a question, Mr. Ali?
السلام عليكم. علي اللويمي.
اللويمي سوري. اللويمي سوري.
السلام عليكم دكتور.
اهلا اهلا. تفضل مستر علي.
Quick simple question. Nowadays, as you mentioned, that cybersecurity, the hackers has become more advanced and they are using different techniques, and we are having attacks from every way. Mostly the attackers get their victim by silly mistakes from the victim himself. For example, they pretend to be the company itself and ask for a password or an update, or sometimes they try to log in to your device, to your account, and the company by itself, for example, Google, will send you a warning. Sometimes even this warning you don't trust, because me myself, one time my email was stolen in this way. I get a message that someone is trying to log in, and it asked me to change the password. When I changed the password, actually it was the hacker page, and it was sent to the hacker, and he stole it. So how we protect ourselves from these silly mistakes, let me call them, if I can mention them as silly mistakes or simple mistakes. If we focus on big things and the more sophisticated ways, but we forget about the small, silly things. Thank you.
Excellent, Ali. That's wonderful contribution. I thank you very much. Definitely, credential theft is one of the most successful thing hackers are able to do it. And you're right, it's because of the social media, whether it's Facebook, whether it is email, or maybe an adware type. You know, you are using your computer and all of a sudden a pop-up screen of an ad, and then you click on it, and then now you enable basically an executable file to run in your machine. So the best prevention, in my opinion, is you have to maintain as a computer user the due care. There is something called the due care, meaning that you have to be very careful whenever you are receiving an email message. Hover on that URL, authenticate. It claims that it is from that source. Don't click on things that you don't trust. Watch out of simply your mode. When you are too tired and you are utilizing the computer, that's when most mistakes happen, because you are not focused, and or maybe you are too busy, and then you click on the wrong thing. And once you do that, you give out your soul, your credentials. And that gives the hacker the ability to simply enter your computer. That's why well-respected companies, they do have a lot of protections measures in the phishing domain. They have gateways. They will scan and validate the different DNSs. The ones that are most problematic in the industry, they will block them. But at home, and or maybe on your phone, sometimes, honestly speaking, we don't really do our part. So we have to be careful. My recommendation, if you are in the enterprise, we need to make sure that all the bells and whistles, all the solutions that have to do with having a phishing type email and or browser access to be going through a gateway to be protected. At home, I don't recommend that you use the same computer as your kids. Make sure that the computer that you are used to do your e-banking and important stuff to be with the latest antivirus, not accessible by younger kids, because we know what happened. Okay, younger kids, they play video games and they don't pay attention, and they invite a lot of malwares to our family desktops. So these are my recommendation of how we handle this. Thank you, Ali. This is excellent. I overlooked to highlight this because this is one of the most important means hacker use in theft, in credential theft. Next question, please.
Okay, thank you, Dr. Salman. عندنا دكتور محمد ظاهري.
Yes. Do you hear me?
Yes, we can hear you.
Okay. Thank you, Doctor, for this presentation. And I'm just curious, like since I am studying control and automation, and I would like to know, where is the industry going, basically? For example, like you mentioned that the machine learning ability to detect the anomalies and etc. And I would like to know, like, I'm not sure if you are familiar with the control like with control systems, like because there are some attacks where you basically, as Mr. Mohammed in the previous presentation mentioned, that by looking at the cyclic behavior of the sensors, like for example, for the level tanks or anything, like you can detect the anomalies, like if it's not happening in that, like in that period of time or in that level of threshold. So I'm wondering, like, what if you are not able to see this behavior, like, because now the attacker will attack or will manipulate the sensor value and the control element at the same time. We know that for the LTI systems, like there is the superposition property where if you have change in the output, you can see it in the input and vice versa. But what if the attacker changes the behavior of the input and the level sensor, and thus you will not be able to see anything in the communication network layer. Thus, you will not be able to apply any classification method like machine learning or anything. Like, what are the industry doing for such things?
Sure. I have an extensive experience in the ICS from applied science, and my PhD is in real-time systems. So I can just tell you from an industry, there is major trends in having cybersecurity intertwined and or embedded in the industrial system. In fact, the safety system now, whenever you are doing a HAZAP study, cybersecurity is now being considered. Even from an international standard perspective, the standard 6115 now simply calls for having cybersecurity to be part of these ICS systems that we deploy in the field. So the industry now, trends-wise, cybersecurity is being a crucial element of the overall end-to-end design. It is being looked at as important as the valve itself, the logic controller. Said that, the vulnerability of changing, quote unquote, manipulating the data, which meaning data integrity, that is a cyber risk. What can we do about that? There is a trend right now where we are saying that take cybersecurity down to level 1, down to the actual sensor level that is managing the process. If you do that, then you have to do an upscale in the actual instrumentation technology. We will have to have these instruments that we have today becoming chip-oriented, firmware-oriented, meaning that we have to have the cybersecurity embedded in them at that level. That's where we're going into the future. There's a lot of discussions right now. I am part of some of these industrial standardization committees where there is a huge debate about sensor to the cloud. Because when you are talking about sensor to the cloud, you are simply taking that sensor directly to the cloud where you have all the automation aspect being processed in the cloud. And the sensor is becoming like a dumb device just sending data. So if I manipulate the data at the sensor level and or maybe man in the middle, somehow I can intercept that communication between the sensor and the cloud. I will be inflicting the same danger as somebody who is doing it in the field, right? So what can be done? It's all about taking the sensor to the next level, more intelligence. Remember, cybersecurity, it's all about not just the technology itself. There's something called the organizational aspect, process and people. There's also something called physical security. So if I have a sensor in the field, to ensure that nobody go in and alter the data, I have to have the physical security aspects of it being addressed. I don't go ahead and put basically an instrument that's very vital to my process in an unlocked cabinet or secure room. So taking the different type of security solutions together and weave them together, whether it's a technology, process, or people, should address the concern that I have. The machine learning is all about behavioral learning. Once the system learns the different variations that instrument simply operate in, an anomaly that is being detected will be flagged. Now, sometimes you go into an error. Can we take error data to make major decisions? Okay. That's where we have to simply bring other solutions like data validations, reconsolidations. So, I mean, it's an end-to-end process where you have to inject different solutions to say, wallahi, I'm going to go with the machine learning and let the plant run in its own. The final comment I have for you is, with all the automation that we also have the human who can override. So if the vital signs of the plant becomes imbalanced, somebody have to go in and override to ensure that we are basically safeguarding the investment. I hope I answered the question.
Thank you very much, Dr. Salman. And thank you for the audience for their question. And let's go for the third presentation. We are now 14 minutes after the time. Okay, thank you very much, Dr. Salman.
Thank you.
The second presenter will be Dr. Abdullah Al-Halafi from Saudi Aramco. Are you here, Doctor?
Assalamu alaikum, good afternoon. Yes.
I'm sorry, Dr. Abdullah, for this. We take your time here. And let's at the beginning. Dr. Abdullah will give us a presentation about digital techniques or technologies for transmission, construction, capital projects in petrochemical industry. We will discuss three recent technologies, namely will be digital twins, Edge AA, and industrial Internet of Things. Just something about Dr. Abdullah. He comes with more than 20 years of experience of several industrial and academic and research experience from SABIC to ABE to Saudi Aramco. He holds a PhD from KAUST in electrical engineering, especially in wireless communication networks, MS from University of Glasgow in electronics and electrical engineering, PhD from KFUPM electrical engineering department. He has been with Saudi Aramco for 11 years and currently been leading major digital transformation programs, including digital twins, implementation of IoT Edge AI for safety application. And he already published several papers in IEEE. And the floor is yours, Dr. Abdullah. And sorry for latency.
Assalamu alaikum, good afternoon. Until I give this shared screen setup, I would like to thank the organizers from KFUPM Institute for Knowledge Exchange for giving me this opportunity. Please allow me to just do the setup for the sharing of the screen. So please confirm if you're able to see my screen.
Still not yet.
How about now?
Yes,
Yeah.
you can see now.
Excellent.
We can see now, Doctor.
Apologies about this delay, but it was just for the system preferences to allow Zoom to do the recording. So to you, respected guests and dear audience, it gives me the pleasure today to talk to you about the digital technologies to transform and enhance the engineering and execution of capital projects in the petrochemical industry. So what is this all about? We're hearing IoT, digital twin, digital transformation, smart factory, IR 4.0, lots of these buzzwords. So are these just new buzzwords in the technology world, or are we also hearing the edge AI? So hopefully the people who are familiar with the Al-Jabal cliffs in KFUPM, hopefully you're not falling any of these cliffs. So I hope by the end of this talk, we will be able to figure out together if this will revolutionize and change our lives and the way we perform industrial operations in particular. So we might have been asking ourselves if we are doomed by the marketing hypes of these modern technologies, or is this just another passing fad? So let's find out together what they mean first. And honestly, coming after those great speakers like Dr. Suleiman, Professor Eric, and the other outstanding speakers, it gives me a bit of challenge to cope with their excellent presentations. So many industries are accelerating the adoption and scaling up of disruptive and multi-purpose digital technologies brought by the fourth industrial revolution to deliver safer, cost-effective, and efficient capital project capabilities that employ advanced levels of artificial intelligence, machine learning, and offering unified engineering models in the early phases of engineering the physical assets. 3D design reviews, project construction monitoring, and automated health and safety surveillance, and also not to forget the sustainability and the environmental monitoring, while also achieving the optimization of overall project management processes, but not to forget the extension of what is developed during projects to continue to be consumed and achieve sustainability in operation and maintenance beyond the completion and handover of the project to create what is known to be the smart plant or the smart factory. So during the digital transformation journey of large organizations, the information technology teams, the operation technology, and even the engineering technology teams are meant to come together, have a better understanding and familiarization of each other's functions and requirements, and capitalize on challenges to create opportunities, collaborate in piloting technologies or deployments of solutions, and have a more of an open discussion on the new transformations. Looking at the fourth industrial revolution as defined by the German Federal Ministry of Education and Research, it says Industry 4.0 is an intelligent production with sustainable engineering methods and interconnected production facilities in smart factories. It's envisioned to provide perfect, autonomous, and more effective production processes, optimized and harmonized logistics operations, and more of a customer expectations-based behavior. The integration of data is looked at to be possible with the industrial Internet of Things by transferring the physical world to the visualized world. Among the many other 4IR technologies such as Internet of Things, UAVs, robotics, cloud and edge computing, smart plants, robotic process automation, blockchain, 3D printing, and advanced analytics. Those technologies pave the road to create the smart factory. And we consider digital twin to be one of the major foundations for the digital transformation and the smart factory. So the smart factories are looked at to be moving towards prediction-based, self-healing, and auto-operating factories for improved productivity, increased workplace safety, and reduced environmental impact. Let's talk more about digital twin to understand it more. We can define digital twin as the digital or virtual representation and actual behaviors of physical assets, systems, or processes that are integrated together as a single source of truth. It integrates various specialized solutions from information technology, IT, engineering technology, ET, and operational technology, or well known by OT. Its implementation enables transforming the contextual and operational data from projects, assets, processes, supply chain, and buildings into accurate, holistic, and useful insights, as well as providing future predictions through a single source of truth that is most updated, unified, and trusted. And we will start to look at some of the pioneers and first people who coined or identified the digital twin. Here we see Dr. Michael Greaves, currently the executive director of the Center for Advanced Manufacturing and Innovation Design in Florida Institute of Technology, who coined that term back in 2002. And you will see throughout this presentation that I will be mentioning some of the first people who coined different terms. Hopefully this will give motives to my dear audience, either from KFUPM students or researchers or professors or ourselves here, to be out there and to lead the way in innovation and design thinking. So looking at the digital twin concept to be more of a data-centric end-to-end paradigm that integrates several digital solutions and covers the full asset life cycle from inception to retirement. It uses various edge digital solutions, devices, software and hardware to enhance and optimize the engineering, procurement, and construction of projects, and to extend to sustain efficient and reliable operation. So as to say, design the asset, procure it, build it, operate it, before operate and maintain it, test it, commission it, and then operate and maintain it sustainably. And at the end of its life cycle, properly recycle it. The dimensional digital twin models is a new term that covers the areas to visualize, virtualize, and optimize the asset. So 3D is simply an intelligent way of representing the physical assets digitally in a graphical formats. It enables the visualization of projects activities, serves during design, procurement, construction, cost and schedule, safety monitoring, and asset performance. The fourth dimension is for time schedule. And we see also here the fifth dimension is for cost, sixth dimension is for safety monitoring and control, and the seventh dimension is for performance during the project execution. Those dimensions serve in different functions for progress or cost or safety or overall performance management, to monitor the progress and logistics and integrate that with costs. And when we are in operation phase, it is used, some of these dimensions are used to improve the schedule or the cost during the maintenance, turnover, and inspection activities, or best known as T&I activities. Add to this the eighth dimension during the facility operation, which is the refers to the environment, to maintain the operation safely and ensuring the environmental compliance and improving the performance and reliability of the asset. So we see here up to 7D during projects and construction, and the eighth dimension is added in the operation phase. Major developments that embrace the data-centric approach for digital twin are envisioned to realize some of the benefits, like design data auto-validation and standards auto-compliance, providing real-time tracking on project schedule and cost, mitigating risks and predicting project health optimization and root cause detection, enabling the engineering design review to be held over 3D models, and to ensure seamless handover from one project phase to another. Simulation of project site activities for constructability reviews, construction quality, health, and safety monitoring, virtual commissioning for startup preparations and 3D inspection walkthroughs on a virtual basis, and for sustaining efficient operations and reliable assets.
Excuse me, Doctor.
Yes, please.
I think one of the attendees should be mute. There's some noise. I'm sorry for interrupting you. Please be mute.
Yeah, sure. Thank you for the announcement. Now we will be talking about edge artificial intelligence. So looking briefly at the history of artificial intelligence to give you some sense. So from the first days of human existence, one of the inherited characteristics is to learn and then teach. So Adam, as a superior, was given this ability to learn all the names, and then he was told to teach the angels their names. And this continued throughout the ages. So we see that human trained animals, but that did not seem to be enough. They wanted to make their own creation and then train it. They, for example, here we look at the Chinese Yanxi and his the creation of the artificer, to the Heron of Alexandria, to the early Arab engineers like Al-Jazari, who's considered the father of modern robotics, where he built the automated robotic musical band, trying to teach that creation. Among many of the other programmable inventions that led to the modern science and engineering and developing today's automation world. Later, around the 1940s and throughout the 50s, that was when the first AI researchers began discussing the possibility of creating an artificial brain, the time of the early computers. And then around the 1950s, the Turing test, in his paper, Alan Turing proposed that machines can think. And he was working on the Pilot A, so the automatic computing engine. He is considered one of the founders of computer science. At the 1956, a handful of scientists, including Nathan Rochester and the famous Claude Shannon, or the information theory pioneer. We will come to see Shannon later on. He's well known in communication engineering for deriving his mathematical formulas for the channel capacity limit and the bandwidth efficiency. By this, he was laying down the foundation to realize the benefits of edge AI, which we will see later in this talk. So those scientists gathered and suggested that every aspect of learning or any other feature of intelligence can, in principle, be so precisely described that a machine can be made to simulate it. So coming back to this idea of machines can think. And among them was John McCarthy from Stanford University, who first noted the name artificial intelligence for his field of research. He claimed that AI is the science and engineering of making intelligent machines, especially intelligent computer programs. So by that broad definition, almost any computer program that makes decisions can be considered AI, even if it is just a collection of if, then else statements. So for example, you might consider a thermostat that turns on the air conditioner if it gets too hot as a form of AI. Most people consider AI also as mimicking human thoughts, where we get to the idea of machine learning. We see here that Sophia is the first social robot who received her citizenship from Saudi Arabia. So a bit of a quick history. Then now we're coming back to the machine learning when it was started. So on March 1949, Shannon presented a paper called Programming a Computer for Playing Chess. And 1 year later, many other researchers started writing game-playing programs for chess and checkers. One of them was Arthur Samuel, who developed a number of algorithms to teach a computer to play checkers. And he did that to make it better than he played. So he had it play thousands of games against itself and learn the best moves. This work actually led him to publish a paper, and he first coined the term machine learning. So when you see machine learning, you see also Arthur Samuel as the first. By the early 60s, machines started to achieve good skills to challenge some of the respectable amateurs. And this field developed further as Professor Tom Mitchell in his machine learning textbook said, we will define learning broadly to include any computer program that improves its performance at some tasks through experience. So being put more precisely, a computer program is set to learn from experience E with some class of tasks T and performance measure P if the performance at that specific tasks measured by that performance improves with experience. So the point here is making improvements. And you can see here by 1997 that machines defeated the world champion in chess. In other words, machine learning is an application of computer algorithms that get better at some task or function based on previous attempts at that task. In a sense, it is a computer program that learns from experience, much like humans and animals do. From this, we can see that machine learning is a subset of artificial intelligence. So all machine algorithms or machine learning algorithms can be considered AI, but not all AI algorithms can be considered machine learning. So, all right, there are many machine learning algorithms out there. One that is getting lots of attention recently is the neural network, which is modeled after how the human brain works. So each of these circles represent a node or a neuron, which performs some algorithms on its inputs and produces an output. The input layer of nodes can take in some samples from something like words in an email or pixels in an image. And the output from these nodes are fed to one or more layer, known as the hidden layers, which is fed to an output layer. So in this example, we might be interested in knowing that the words in the email indicate that the email itself is a spam, or that the image is a cat. So the output node can give us 0 for not cat, or 1 for cat, and so on. We can have more output nodes if we need to classify more than one thing. To train the neural network, we assign a number of weights to each of these connections. Whenever a node produces an output, which is just a number, it is then multiplied by that weight before being fed into the next node. So we might feed pixels to the input layer and all those weights to determine the ultimate output. If the model was wrong at guessing that the image was actually a cat, we would penalize it and then train the algorithm to adjust the weight and try again. We do this hundreds or thousands of times until the model can successfully get to the correct input image, which is a cat. So at that point, we have a fully trained neural network. Most machine learning models work like this. So a model is just a collection of numbers, weights, in the case of a neural network, and which map to which operation we should perform. We run one more algorithm to train the model. That is, we adjust the numbers that make up the model until the output of the model is giving us what we expect. The idea of adding more than one hidden layer to these models is not actually a new concept. It has been around since the 60s. So adding more layers will help often with accuracy, but it comes with more computationally intensive with each layer added. So by the 1986, Rena Ditcher introduced the term deep learning in her paper to describe similar added complexity in depth in other machine learning models. So as a result, we arrive at the notion that deep learning is again a subset of machine learning and a bigger subset of the, or a subset of the bigger artificial intelligence. Unfortunately, for many years, deep learning remained in the fringes, locked away in universities and research centers. That was until Google Brain was formed, a research team back in the 2010 to work on making deep learning more accessible. So 2 years later, they made a big splash by showing they could train a rather complex neural network to recognize images of a cat. So they did not do this on distributed images, but they did this by feeding it with millions of images found on YouTube videos. Also around the same time, we saw the rise of graphics cards being used for machine learning. So while a CPU core is optimized to perform one operation on one or two pieces of data arrays very quickly, graphics card is capable of performing one operation across thousands or millions of pieces of data at the same time. And this is how they update the images on your monitor so quickly. So as it turns out, this is a super useful for performing matrix operations found in many of the machine learning algorithms. We're now also seeing the custom circuits being designed in FPGAs and ASICs to perform these algorithms even more efficiently. Thanks to these efforts to make deep learning more useful and accessible, we are now seeing an explosion of machine learning applications in many fields. So from robotics to medical devices to marketing to even industrial applications. And people are realizing that you can throw machine learning algorithms at data to discover patterns, for example. Facial recognition is one common example, but many social media platforms are now using machine learning to figure out which post to show you to keep you engaging more, and it's working. I hope I am also keeping you engaged with me in this talk. So at the time, after about 2012, another popular buzzword became the big data. As companies started to realize they can apply machine learning algorithms to help grow their businesses, they wanted to get their hands on every piece of data imaginable. So for example, collecting the browsing habits of thousands of users required large amounts of data, terabyte potentially to be stored on servers. And you might need then to transfer all this data to a separate server if you want to run machine learning algorithms to predict what users will search for or buy next. And this gave a rise to the notion of collecting, storing, and managing big data. That should hopefully give you an overview of what machine learning is and when it was started, an idea of what this notion of deep learning is all about. But there is one more thing to throw into this table, which is the Internet of Things. That's another buzzword that you couldn't stop hearing about in the last couple of years. Connecting embedded systems to the internet is actually not really a new concept, as the first IoT device we see on the bottom corner here was the Coke machine in the Carnegie Mellon University back in 1982. But by some forecast, we should have around 50 billion internet-connected devices around 2030. While some of the applications sound silly, but when it comes to industrial Internet of Things, it's becoming very useful for industrial automation applications where things, robots, sensors can be remotely monitored and can report potential problems before they happen. And that's possibly saving operations millions in costly repairs. So once again, we run into the problem of having to collect, transport, and analyze all that data. So let's say you have got some internet connected sensors in your plant, and they are sending gabs and gabs of data back to some server across the internet or into an organization or corporate IT network where you are running some fancy machine learning algorithms to try and predict either production throughput or maintenance needs or whatever else. All these meaningful statistics are sent to a dashboard on the central control room, to a corporate center, or to an office computer, or even to the manager's mobile device, where the boss can determine which actions to take next from the comfort of his office. This is one example of the idea of cloud computing. However, as you begin to scale up operations in your plant, you might start to run into physical limitations in your network bandwidth. And if you remember the Shannon limit theorem that we talked about earlier, so your network will get too crowded with those sensor data and will compete for extra bandwidth. That's where you get to the idea of edge computing, where you run your own local computers or servers to help manage all that data. These servers do not exist out in the cloud. You're likely to own or have control of them. So they are set to be located at the edge of the cloud. They might not be as powerful as the remote servers, but they can help alleviate some of the bandwidth requirements. And these servers can collect, organize, and do some basic analysis of your data before shipping it out to the remote server. And here is where the fun begins. If we start running the machine learning algorithms on that local server, we have entered into the realm of edge AI. Even if the algorithms are not as accurate or as fast as they would be on that remote server, they still be more useful being closer to the collection devices, other than having to rely on the internet and all of its latency, congestion, and noise. And also to consider the cybersecurity aspects of this. It gets more interesting when we start running machine learning algorithms on the field devices themselves, assuming that they have the necessary processing power. We can do some basic data analysis and curation of the data before sending it off to our remote servers. So if you're looking for a more familiar example of edge AI, just howl on Alexa or say, okay, Google. Another interesting application is to check for how self-driving vehicle sensors function. So would you sacrifice waiting for the cloud through the internet to tell your vehicle that there is a camel or a deer passing in front of it? Or do you insist to have that analysis embedded into the vehicle itself at the edge? So I think you got the idea by now. As a matter of fact, I hope edge AI for projects construction, monitoring, and IoT applications is becoming more clear to your understanding. Not to forget its importance for future critical applications such as machine-to-machine communication and vehicle-to-everything. We will be talking next about the Internet of Things in more detail. So reference to the IEC 20924 and the international standard IEC 30414 as a standard naming and reference architecture. The Internet of Things is an infrastructure of interconnected entities, people, systems, and information resources together with surfaces which reacts to information from the physical and virtual world. So that's by definition, showing here that we are allowing tight and seamless integration between lower layer components of your field devices and systems, such as sensors and actuators, to the higher levels connected with either the enterprise or the internet and cloud platforms. In this slide, I'm trying to show here the main differences between the non-IoT based and traditional control systems to be predefined, structured data, which normally requires structured and predefined decisions. While in the IoT approaches, we are dealing with unstructured data, and the data acquisition is spread across heterogeneous sources, and that will need and require more intelligent processing of gathered data, and which makes it more challenging for data transmission management and crowd sensing. Some of the challenges that I can talk about in the industrial Internet of Things deployments for large-scale plants, whether it is petrochemicals or oil and gas, that if they are coexisting and the harsh and complex networks that are already available in the legacy systems. Developments in the communication technologies and protocols and standards, the requirement for optimization and intelligent processes, the interaction between the physical and virtual world, the wireless connectivity and layout and design, the remote programmability and diagnostics, also not to forget the safety, security, and environmental ecosystems. And one more thing to throw into this, these challenges is the establishment of an energy efficient wireless sensor networks. Addressing the last point of this, we have done quite a bit of a good research in this area, which is the energy efficiency and the IoT networks. You can refer and look up this protocol, the Green Task-Based Sensing, which is published in InfoComm back in 2016. It actually discusses a cross-layer approach to optimize the energy consumption in a wireless sensor network. Having an integrated systems and the wireless connectivity provides observability, control, and analytics, as well as the safety of industrial operations. However, there are what we have seen also today morning from Mr. Tushar's presentation, I think, or Mr. Mohammed's from Emerson, talking about the wireless heart and the ISA 100 wireless. These are the current wireless communication technologies used in the industrial domain. How about if we think about 5G networks and 4G LTE? What protocol developments and what cybersecurity needs to be implemented? There are a lot of efforts done by the Internet Engineering Task Force and also the IEEE and the HC standards bodies to look into several developments across the protocol stack, from the link layer to the internet to the transport and application layers. Here is a key internet protocol, the IPv6. How large is that? Is the header of the IPv6 will determine how efficient is the transmission and how energy efficient is that transmission. Research opportunities, looking at some of the suggestions or recommendations to have an middleware approach to provide a new way of data management and to facilitate adaptability, task sharing, real-time monitoring, and to have more of a location awareness. There are opportunities to do further research in the connection management, traffic and flow classification and awareness, and also for the cloud sensing. There is a lot of research around the different network layers, and also to consider the cybersecurity aspect of this. So this is a call to our colleagues in the research community and the students to look into these aspects. When it comes to capital projects, wrapping up this talk, the digital solutions that should provide a single visual interface for construction sites, and one of the issues that I can think of is the real-time equipment location and tracking, usage and performance monitoring. How can we do this with the support of the IoT and edge analytics, the safety and health monitoring of personnel at construction sites. So looking at, for example, managing the congestion laydown areas across the busy large construction sites, the planning of heavy equipment moves and oversized deliveries. So with this, I conclude my talk. I hope I gave you an overview of what are the new technologies that are used for improving and enhancing the capital projects in the petrochemical industry. Part of it is the digital twin to be created in early phases of engineering that specific asset, and building the engineering foundation to extend beyond the project delivery to cover and enhance also the operation and maintenance. I also talked about the edge AI and how is this related to machine learning and deep learning and neural networks. And I also talked about the Internet of Things and the main research opportunities and challenges in there. With this, I conclude my talk and open the floor for any questions. And thank you very much.
Thank you very much, Dr. Abdullah Al-Halafi, for this very interesting presentation. Now I will open the floor for the question from the audience.
I have provided at the end of the presentation my email. So in case further discussion is required, everyone is welcome.
Okay, thank you very much.
Thank you so much.
Yeah, if you have any question, audience, you can send any comments or any question to Dr. Abdullah through his email. Inshallah, we'll share it with you. I think we have one question here. Okay, just a comment. Okay, any question? Okay. Okay, thank you all of you. Thank you, Dr. Abdullah Al-Halafi, for this nice presentation. I hope we can see you soon, and we have another presentation from you. And thank you for sharing this experience with us and sharing good information with the audience as well. I think at the end we want to thank all the presentation here, Dr. Mujahid.
Okay, yes. Okay, thank you very much, Dr. Nizar. Okay, good afternoon, everybody. So I would like to just conclude. So first and foremost, I would like to express my appreciation to the distinguished speakers for their valuable contribution to our forum on recent advances in process instrumentation and control. Over the last half day, my deepest gratitude goes to all who attended the forum and helped to make it such a successful event. The organizing committee is mandated to keep you updated on the latest developments in the control and instrumentation industry and research also. Hearing and learning from speakers as well as the audience has educated myself and all of us, as I guess, on how digital twins, self-deprecating robotics, pervasive sensing technology, industrial control systems, cybersecurity protection, artificial intelligence, and industrial Internet of Things, how these things can help to advance process instrumentation and control. I would like briefly to review some of the main points aired during our deliberations. It was clear that digital twins provide early warnings for any performance deviations for proactive interventions, and acts as a decision support tool that enables improved safety, reliability, and profitability in design as well as operations of the plant. Also, it was clear that adopting innovative sensing technologies that are easy and cost-effective to install and maintain is crucial to advanced process control systems. Also, we concluded that cybersecurity is an essential building block of the overall safety and integrity of industrial control systems, intelligent infrastructure. And also, we have seen that digital twin, age, artificial intelligence, and industrial Internet of Things will advance the execution of engineering and construction for capital projects in the oil and gas sector, as well as chemical industries. Finally, I would like to emphasize that it is important to regularly hear the views from industry and academic experts on their recent challenges and suggested solutions. I hope that what we hear today helped us to have better understanding of the rapid challenges and changes in this very important sector of the global economy. I am certain that takeaways from this forum will further deepen our thinking and stimulate our work for the future. Thank you very much. Thank you for listening, and hope to see you again in other events.